Hello everyone. In this lecture, we will be introduced to DevOps as a term. I am aware that most of you already have an understanding or perhaps a formal definition of the term. But to be all on the same page for the rest of this course, let's define the term and get to know a little bit about its origins. When you hear the term DevOps, what's the first thing that comes into your mind? A set of tools and technologies? A job title or description? A department? Or perhaps a mix of all the above? Well, although DevOps today is regarded as a good-paying, highly demanded job, technically speaking, it is much broader than that. DevOps is a cultural movement that was coined around the year 2007. It aims at bringing developers and operations to work together in collaboration. It can be considered a direct result of the Agile software development methodology. If you're not familiar with it, Agile is a way to decrease the amount of development time and release software more frequently. It has many principles that cannot be all discussed in this lecture. We just need to know that a project is developed in small increments called sprints. Developers, operators, quality assurance, and even information security teams should collaborate on the same project. There should not be any barriers between the teams, and thus they should not be operating in dedicated silos. To achieve this, several periodic meetings should be held between all the teams. For example, daily stand-ups, sprint planning, review, and retrospective, to name a few. Agile also encourages following best practices in code development. For example, CI/CD. CI/CD is a topic that deserves its own lecture. It stands for Continuous Integration, Delivery, and Deployment. As we will see later in this class, CI/CD seeks to always keep the software in a deployable state. Test automation, which constantly runs unit and integration tests against the software. Rapid feedback from the customers. This is done through filing issues in the software's repository, joining Slack channels, and other means of feedback collection. Constant monitoring of the application and the underlying infrastructure through dedicated systems like Prometheus, Datadog, and others. This is made possible with the help of many tools that exist today and that continue to evolve. I am mentioning a few of the most popular ones here. For example, we have GitHub, GitLab for CI/CD, Terraform for infrastructure as code, Ansible for configuration management, Docker and Kubernetes for containerization and container orchestration, among many others. Thus, I guess by now we can have a more concrete definition of what DevOps really is. It is the collaboration between developers and operators that is done within a set of best practices assisted by software applications. It can be considered a direct result of following the Agile software development methodology. Hundreds of tools are used today to make it easier for DevOps to be implemented. So, at the end of this video, we can regard DevOps as a combination of Dev and Ops collaboration that follows best practices in Agile software development backed by tools that make the whole process easier. That brings us to the end of this lecture. Thanks for watching. Hello everyone. In the previous lecture, we had an overview of what DevOps stands for and how it came into existence. We've also mentioned some of the best practices that the DevOps movement follows, including CI/CD. In this lecture, let's spend a few moments shedding some light on this topic since it consumes the sheer amount of a DevOps engineer's time. CI/CD is an acronym for Continuous Integration, Continuous Delivery, and Deployment. Let's discuss each of those terms separately. We start with the CI or Continuous Integration. CI entails checking the application for possible bugs or failures whenever code gets pushed to the repository. Since many code commits are done per day from different team members, this test should be automated. It also should be done as quickly as possible so that if some issue is detected, it gets resolved quickly before more commits are added on top of it. A typical CI pipeline is made up of the following: a code repository where code is stored and version controlled. Git is the most popular version control system around today. However, it is not the only one. There are other tools like Subversion, ClearCase, and others. We also need a well-defined workflow that all engineers follow. For example, no one pushes code directly to the main branch. Instead, there should be a pull request that gets peer-reviewed first. We will discuss that in greater detail later in this class. Finally, we also require a build server that automates the whole process. Today, all major Git repository services already provide a CI pipeline as an added feature. For example, GitLab has GitLab CI, GitHub has GitHub Actions, Bitbucket offers Bitbucket pipelines, and AWS has its own code build and code pipeline service. When it comes to the workflow, it can run as follows. The developer makes changes to the code, perhaps adding features or fixing bugs. At least once a day, the code is pushed to the repository. The developer raises a pull request, sometimes also referred to as a merge request, to merge their code to the main branch. Once the PR is raised, the CI server is notified. It builds the code if necessary and runs one or more checks against it. If all the checks pass, the code can be safely merged with the main branch. Often, there's also a peer review step where another team member reviews the code and may request changes. If everything goes well, the code is merged with the main branch. But if the pipeline fails, this means that the code failed to satisfy one or more checks, or maybe it even failed to build. In this case, the developer is notified with the errors. They need to fix them and push the modified code back to the repository where the CI pipeline gets triggered again to make sure the modified code addresses the issues. This workflow can be depicted in this diagram. As long as the code does not pass all the checks, the developer has to keep on making modifications and pushing back to the repository until the code is clear to be merged. The advantage of CI is that faulty code is never merged to the main branch. Developers always have almost immediate feedback about their code quality and the presence of any bugs or issues. But what happens once the code gets merged with the main branch? This is where CD, or continuous delivery, kicks in. In this phase, we need to make sure that the application is also deployable to environments that are as close as possible to production. This is a vivid example of how dev and ops come together. When developers push their code to a repo, the code is not only tested against quality issues, but also against deployment ones. The deployment process itself largely depends on the application and infrastructure types. For example, deployment can be just uploading the files to the server through FTP or rsync, then restarting the servers. But it could also get more complex, like running pre- and post scripts, changing file permissions, adding users, and so on. In this case, CD needs to work hand in hand with configuration management tools like Ansible to automate complex deployments. If the environment is based on Kubernetes, specialized tools like kubectl, Helm, or Kustomize are used. Once the deployment is successful, this proves that the code is deployable, but still more tests should be performed. CD tests are of special importance if your application follows the microservices architecture. The reason is that CI would typically run tests against a single service or API, assuming that each service is hosted in its own repository. However, when the application is deployed to an environment, the deployment involves deploying all the services and APIs. The application here is tested in whole, end-to-end, and user acceptance tests, which are also referred to as UAT, are performed. For that reason, you will often find organizations running CD immediately after CI, hence the name CI/CD. They want to make sure that they run as many tests as possible to give developers proper feedback. Obviously, well-crafted CI/CD pipelines should always keep the code in a deployable state. A snapshot of that deployable code should be stored and versioned somewhere so that we can refer to it when we need to. To achieve this, the CI pipeline uploads what's called code artifact to an artifact storage. An artifact is a fancy word that describes a code bundle with a specific version. That bundle could be a simple zip file containing the code files in compressed format. Some programming languages have their own way of building code. For example, Java uses jar or var files, Ruby uses gems, C and C++ compile to binary files, and so on. If you are using Docker, then the artifact should be a Docker image. In all cases, the artifact is uploaded to a special storage called the Artifactory. Again, this is a fancy name for any place where you can store files in versioned format. You can use Amazon S3, JFrog, Nexus, or others. The important thing to notice here is that the artifact that gets tested and uploaded to the Artifactory the first time should remain the same throughout all the remaining steps in the pipeline, including production deployment. The reason is that we want to make sure that this artifact is the very same one that passed all the configured tests. After everything passes successfully, code is now ready to be deployed to production. However, this step is performed manually. A button needs to be pressed by a human who selects which artifact will be released to production. In more advanced environments, this step is also done automatically. This process is referred to as continuous deployment. Nevertheless, and due to the risk of deploying faulty code to a live system, more vigorous tests are performed. For example, functional tests, performance tests, and stress tests. Additionally, a continuous deployment pipeline should have the proper mechanism of rolling back a failed deployment and returning to the previous working state. One way of achieving this is by using feature gates, where certain capabilities of the application can be turned on or off without having to redeploy. Another popular way is using blue-green deployments, which we will touch base with later in this class. So, in this video we discussed in some detail the CI/CD process, which is an integral part of DevOps. We also explained the difference between continuous delivery and deployment, which sometimes are confusing for beginners. That brings us to the end of this lecture. Thanks for watching. Hello everyone. In the previous lecture, we discussed one of the main pillars of DevOps, which is CI/CD. In this lecture, we are going to shed light on a less known topic that is gaining a lot of attention quickly, which is IAC, short for Infrastructure as Code. Let's start as usual by the definition. Infrastructure as Code is the practice of building, managing, and deleting infrastructure components through code. The practice is quickly being adopted in many organizations together with DevOps. The reason is that the same best practices that are used by DevOps can be equally applied to IAC, like CI/CD for example. Additionally, since we are using code, we can use version control systems like Git to maintain it. This would bring the benefits of using version control workflows like peer reviews, requiring pull requests to guarantee code quality. Furthermore, and since the infrastructure is analogous to the code stored in the Git repository, we can have a clear view of what has been applied and when by simply viewing the Git branch tree and log. If we want to roll back a failed deployment or even switch from one environment version to the other, this is as simple as checking out a branch or a commit and reapplying the code. There are three ways of implementing infrastructure as code. First, imperative tools. All major cloud providers offer a tool that can be invoked from the command line to control the infrastructure through API calls that are done behind the scenes. For example, AWS offers AWS CLI, Microsoft provides AZ, and Google Cloud has gcloud. Each of which varies dramatically in their syntax and arguments, but in the end, all of them do the same thing. They take the command, convert it into the appropriate API call, and send it to the cloud provider's API. The API often responds with the command result. It is received by the tool, converted appropriately, and displayed to the user. Each tool can manage all aspects of the infrastructure for the respective cloud provider. For example, this command is used to create an EC2 instance on AWS. It uses a specific AMI image, an instance type of T2 micro, a key pair, a security group, and a subnet ID. Running this command in a command line that has the proper AWS credentials defined will create an EC2 instance with the supplied details. However, they are more suited for carrying out operational tasks rather than infrastructure management and provisioning ones. For example, this command is used to list all EC2 instances of type T2 micro in the current account. The result is a list of instance IDs that satisfy the provided filter. This list can be piped to another command that applies something to each instance. For example, take a backup. The reason why those tools are more suited for operations rather than provisioning and deprovisioning is that they do not store the state of the infrastructure that is built or changed. For example, if we try and rerun the command that creates the EC2 instance, it will attempt to create a new instance with the same specs again. It will have no notion that there is already an instance running as a result of its execution. Things are even worse when the infrastructure gets more complex. A typical software project can have several EC2 instances, a load balancer, an RDS database, and one or more S3 buckets. The lack of saved state here means that we have no way of managing changes to the infrastructure properly. There are many declarative IAC tools today. Some of them are cloud agnostic, which means that they can work with more than one cloud provider. For example, Terraform, Ansible, Puppet, and Chef. There also exist tools that are provided and maintained by the respective cloud providers. For example, AWS CloudFormation. The following is a Terraform code snippet that can be used to create an EC2 instance. Notice that this is a file that can be stored in version control and applied using Terraform command line tool. Compare that to the AWS CLI command that must be run each time from the command line. It's true that you can combine several commands in a script and store that under version control. Yet again, scripts are more suited towards operational tasks because of their lack of state persistence. To better understand what we mean by state persistence, if we make a change to this manifest, for example, modify the instance type from T2 micro to T3 and reapply the manifest, Terraform is already aware that this manifest was already applied before and resulted in an EC2 instance. Reapplying the same manifest with a modified instance type will replace the existing instance with another one of the new type. That is, delete the old instance, then create a new one with the new details. If we attempt to do the same thing using AWS CLI, we'll end up having two instances, one of type T2 micro and another of type T3 micro. It's worth stepping back a little here and reviewing the difference between imperative and declarative type of instructions. I always like to explain them by comparing those two remote-controlled devices. Both can do the exact same tasks, that is, controlling a TV set. However, the way they take your instructions varies dramatically. Let's say that you are currently watching Channel 5, which is displaying your favorite show. A few moments later, you remember that the football game is airing live on Channel 8 and you need to switch channels to view it. Now, if your TV set came with the remote control device on the left, then you would do the following. First, determine which channel you are currently on. It's Channel 5. Calculate how many channels you need to skip to reach the desired channel, which is 8. Push the button with the arrow up symbol exactly 3 times to skip Channel 5, 6, and 7 to finally land on Channel 8. Let's assume that we need to do the same thing, only that you are watching another TV set that uses the remote control device on the right. Now, all you need to do to move to Channel 8 is to simply press the button labeled 8 on the device. It doesn't matter which channel you are currently on. You don't have to determine how many channels you need to skip up or down, and most importantly, you don't need to press the up or down buttons multiple times to reach your target channel. The device on the left used imperative instructions from you. That is, you had to teach the device how to carry out the task. You did the math, subtracted 5 from 8 to get the number of channels the device needs to jump, and sent the skip command 3 times. But on the device on the right, you just describe the result that you wanted and that's it. It's up to the device to determine the best way to reach the target you specified. You don't need to bother yourself with that. Instead, you focus on more important tasks like which channel you need to switch to when the game's over. This analogy perfectly applies to how we can instruct the cloud provider to provision infrastructure for us imperatively or declaratively. The previous example of creating just one EC2 instance may not be very illustrative. But later, when we create complex environments with many components that have dependencies and a build order that must be honored, you will find that a declarative tool like Terraform makes much more sense than issuing CLI commands. Our third type of tools here is CDK and SDK tools. They are more suitable for developers who want to feel at home when working with infrastructure as code. In other words, they allow them to code in their favorite language and still control and manage the infrastructure. SDK stands for Software Development Kits. All modern programming languages provide SDKs for interacting with cloud providers. For example, Python has the Bodo 3 library which can control AWS environments. The main advantage here is that you can code the infrastructure the same way you code the business application. In fact, you can bundle infrastructure code with the application code. For example, the following code snippet uses Python with the Bodo 3 library to create an EC2 instance. The instances variable here will hold data about the deployed instance, like the instance ID, for example. You can make use of this variable in your regular Python code the same way you do with any other variable. But again, SDKs use imperative instructions, which makes them more suitable for operational tasks rather than infrastructure management. To bridge this gap, we have CDKs. CDK stands for Cloud Development Kit. It follows the same approach as SDKs in that it allows you to code in your favorite programming language. But the main difference here is that CDKs are declarative. The way they achieve that is that code gets converted to tool-specific manifest that gets applied declaratively to the cloud provider. For example, AWS provides CDK where you can code in JavaScript, TypeScript, C#, Java, Python, or Go. The code then gets transformed into CloudFormation templates before it gets applied to AWS. Similarly, we have Terraform CDK, which allows you to code in the same supported languages. But the code gets transformed into Terraform manifests instead of CloudFormation. As you can see, the concept remains the same. You code in your favorite language if it is supported, and the instructions are applied declaratively to the cloud provider. So, in this video, we discussed the infrastructure as code concepts in the various ways that it can be applied in. That brings us to the end of this lecture. Thanks for watching. Hello everyone. For the rest of this class, we are going to use AWS as our cloud provider of choice. So, in this lecture, we will discuss how we can create an account on AWS and how to enable programmatic access so that we can issue commands to AWS through the command line. The first thing we need to do is visit aws.amazon.com. If you don't already have an account on AWS, you can click on the orange button labeled Create AWS Account. You will need a valid email address, so you enter it here. Once it is verified, you will need to supply a valid credit card number. You will need to pay attention here. AWS offers some of its services for free for new users for up to 1 year in what's called the free tier. However, not all the services that we are going to work with in this class are subject to the free tier. This means that you may incur charges when you create the labs that we are showing in this class. Now, let's move back to our account creation. Once you supply valid credentials, email address, and a credit card number, you can log in with the email and password that you chose. Notice that the account that you create is called the root account. It is not advisable that you use it for daily AWS activities. Instead, you need to create a user account for you with administrative privileges and use that for your work. Let's see how we can do that. So, once we are logged into AWS, we need to go to the IAM service. Select Users from the left navigation. I already have a user called Ahmed, which I use to log into my account. Let's create a second user that we are going to use throughout this class. So we click Add Users. The username can be DevOps. This user needs to have programmatic access as well as console access. So we check the Enable Console Access checkbox. We have the option to have AWS generate a password for us, or we can opt to create our own. Let's type the password under Custom. And we uncheck the option that the user must change the password on first login. Once the user is created, it does not have any permissions. We can either add the user to a group, copy permissions from an existing user, or directly attach policies. Let's choose the last option. And we select the Administrative Access Policy. This gives the user full access to all AWS services. Finally, we click on the Create User button. The user has been created. We can download the username and password in a CSV file for our reference. The next step we need to do is create programmatic access credentials for this user so that it can issue commands to AWS from the command line. So we return to the users list, click on the DevOps user, and click on the Security Credentials tab. Then under the Access Key panel, we create a new access key. And we use the command line interface option. Click on the Consent checkbox to agree that we want to use this method for working with AWS through the CLI. And click Next. Then click on Create Access Key. Let's keep this page open since we will need those credentials in a moment. Now we need to install the AWS CLI command line tool. So we open a second tab and search for Install AWS CLI version 2, which is the latest version. The first search results comes from the official AWS documentation. That is what we want. The document displays the different options for installing AWS CLI on Windows, Linux, and Mac OS. The operating system that we will be using for the rest of this class is Ubuntu Linux. However, all the tools that we will be using work equally on Windows and Mac OS. So let's expand the instructions for Linux, copy the installation command, open the terminal and paste the command. When this command completes running, we can double check that AWS has been installed successfully by running AWS --version. Now we need to configure AWS CLI to use the credentials of the user that we've just created. We run AWS configure, which will open an interactive prompt asking for the credentials. The first item is the AWS Access Key ID. We copy it from the page and paste it back to the terminal. The second item is the secret access key. Again, we copy it from the page and paste it in the terminal. The final two parameters that we need are the region. We will be operating in the EU West 1 region, and the output format, we will be using JSON. Now, the command line tool is configured to use the DevOps account. Let's make a quick test to make sure that we are able to use the command line tool against AWS. We can try listing the S3 buckets that we have by running AWS S3 list. As you can see, we have a list of the buckets available under this account. This proves that we were able to log into AWS and access the S3 service. So, in this lecture, we were able to create an account for us on AWS with programmatic access. For the rest of this class, we are going to use this user for issuing commands against AWS through the command line tools. That brings us to the end of this lecture. Thanks for watching. Hello everyone. In this video, we are going to briefly discuss what Terraform is for those of you who are not familiar with it. We will also explore the different options by which we can install Terraform to our system, whether it was Windows, Linux, or Mac OS. Terraform is an infrastructure as code tool. It belongs to the declarative type of IAC tools. That is, you create documents that describe how you want your environment to look and behave, and let Terraform determine how and in which order it should create and configure the infrastructure to match your desired state. Terraform saves the state of everything it creates. For example, if you use Terraform to create a load balancer, it records in the state file that the current environment contains a load balancer. If you try to apply the same configuration again, nothing will happen as the load balancer is already created and nothing more is needed. Saving the state allows Terraform to be idempotent. Idempotence means that if you run a command to create or configure an environment, then the action happens only the first time the command is run. Subsequent running of the same command with the same options has no effect. A non-idempotent tool will create duplicate items or may error out depending on the target environment. Terraform can save the state either locally in a file or remotely in an S3 bucket. If you're working with other cloud providers like Azure or GCP, the same concept applies. When you work with Terraform, you write the manifests in a proprietary language called HCL, which is short for HashiCorp Configuration Language. HashiCorp is the company behind Terraform. Terraform is a cloud-agnostic tool. This means that it is not bound to a specific cloud provider. This makes it ideal for creating hybrid environments where components span more than one cloud provider. As you already know by now, this class is focused on AWS as the cloud provider of choice. Having said that, it's worth noting that Terraform can also be used to create CloudFormation templates. CloudFormation is AWS's own infrastructure as code tool. But since it is an AWS product, Terraform can also be used to create CloudFormation templates if you need to. So, this was a brief introduction to Terraform as an IAC tool. Let's see now how we can install Terraform on our laptop. Let's start by opening our browser and navigating to terraform.io. Terraform comes in two flavors: the self-managed form, where you use the tool from your own environment, and the enterprise one, where HashiCorp manages Terraform for you and it is offered in the form of software as a service. For this class, we are going to use the free version. So, we click on the download button. Terraform is written in the Golang language. This means that it can be run as a single binary file on all supported platforms. As you can see, we have Mac OS, Windows, Linux, FreeBSD, OpenBSD, and Solaris. So for Windows, we have two versions, the 32-bit and the 64-bit. The system I'm currently using runs a 64-bit architecture, and I guess yours too. Thus, we click on the AMD64 link. This downloads a zip file containing the binary file. Once the file is downloaded, we can open the zip file, extract the file, then you can just run Terraform version, for example. You can also place this file in a location that is in your path variable so that you can call Terraform without having to specify the full path to the directory where it resides. However, I personally prefer to do the installation using package managers. A package manager takes care of all the tiny details for you, like placing the file in the appropriate directory that's within the path. It can also upgrade the version of the software or uninstall it using predefined commands instead of having to do that yourself. There are many package managers that are available for Windows. For this lab, we will use Chocolatey. If you don't have it already installed, you can just go to chocolatey.org/install. Then you can just copy and execute this command in PowerShell. Just make sure that it is opened with the admin privileges. To open the terminal with admin privileges, you can just right-click on Windows icon in the taskbar and choose Terminal with admin between brackets. I already have Chocolatey installed on my system, so I can just install Terraform by simply running choco install Terraform. Answer yes to the prompts. Once the installation is done, we can double-check that Terraform is installed correctly by running Terraform version. For Linux and Mac OS again, we have two options, either to download the binary file and place it somewhere in your path, or use a package manager. I personally recommend using Homebrew, which works equally on Linux as well as Mac OS. To install Homebrew, navigate to brew.sh, copy and paste the command shown here. You may need to have git installed for this command to work. Once done, you can use brew to install packages as follows: brew install Terraform. Notice that you don't need to use sudo, as brew automatically takes care of that. It will ask you for your sudo password only when necessary. Once the command is done, we can double check that Terraform is installed correctly by running Terraform version. The exact same steps can be performed on a Mac OS box using Homebrew. So, in this lecture we got introduced to Terraform, the IAC that we are going to use in this class. That brings us to the end of this video. Thanks for watching. Hello everyone. In this lecture, we are going to create the AWS user account and role that Terraform is going to use. I already have an account with administrative privileges, so I can just use that one. But that's not the best practice. The reason is that Terraform may need to have less privileges for security purposes. So, one option is to create a separate user account on AWS and use that with Terraform. We can attach whichever policies Terraform would need to that user. But a better option is to create a user for Terraform with almost no privileges. Then we create a role and attach whichever policies that Terraform will need to that role. Afterwards, Terraform can assume that role and start managing infrastructure on AWS. The advantage of using this approach is that when Terraform assumes that role, AWS provides a short-lived token that Terraform can use throughout the process. The token lasts for an hour by default, but we can decrease that if you want to. After the token expires, the user needs to assume the role again and retrieve a new token. Obviously, this adds more security to our AWS access. Additionally, using a role allows you to let users from other AWS accounts assume this role and manage the infrastructure. A very popular use case here is when you have an AWS organization with multiple accounts. Terraform can have a service user in the management account that can assume roles created specifically for Terraform in other accounts, for example, dev, staging, and production. So, now that we agree on how we are letting Terraform access our AWS account, let's create the user and the role. We start with the user. We open the terminal. We have already configured AWS credentials in this shell, so we are allowed to access AWS. We run AWS IAM create user --username, then we pick a descriptive username, let's say Terraform. We don't need to provide console access to this user, only programmatic access will be needed. So we run AWS IAM create access key --username Terraform. The output of this command contains the AWS access key ID and secret access key. We need to copy both somewhere. Now we need to make sure that this user can connect to AWS through the CLI. So we run AWS configure, passing in a new profile. Let's call it Terraform. Having more than one AWS profile allows you to switch users by just changing the AWS profile environment variable, as we will see in a few moments. We are asked for the access key ID, so let's copy and paste that. Then the secret access key, again, let's copy and paste that too. The region is EU West 1 since this is closest to where I live. You may want to use a different region depending on your location. The output format is JSON. Now let's check our work by setting the AWS profile environment variable to Terraform, which is the name of the profile that we've just created. And let's issue any AWS command. For example, AWS S3 ls, which would normally return a list of the S3 buckets that we have in our account. We have access denied, which is the expected result. This message means that the user was successfully able to log into AWS, but it didn't have enough permissions to list S3 buckets. By default, any user that gets created on AWS enjoys 0 permissions. We need to explicitly define which permissions this user can have by attaching policies. In our case, we are only allowing this user to assume a role, so let's create that role firsthand. This role needs to have a policy that identifies who can assume it. This is called a trust policy document, and we need to create it first. A policy is nothing but a JSON file, so let's create a file called trust.json. The name doesn't really matter here. The contents of this file are standard, but you need to pay special attention to the principal part. This is where you define who can assume this role that we are yet to create. We want this role to be assumable only by the Terraform account that we created a few moments ago. So we write the ARN of the Terraform user, and we save the file. Now let's switch profiles to the default profile since it is the one I am using and it contains admin privileges. And run AWS IAM create role role name, let's call it Terraform role, and the assume role policy document is the trust.json file that we have just created and stored in our current working directory. Now our role has been created, but this role does not have any permissions yet. The same as users in AWS, roles are created with 0 permissions. We need to explicitly add them by attaching policies. For the sake of simplicity, we are going to attach admin privileges to this role. So we run AWS IAM attach role policy --policy ARN, and we write the standard ARN of the AWS administrator access policy. Then we supply the role name, which is Terraform-role. Now our Terraform user can have admin privileges, but only when it assumes the Terraform role. But the Terraform user cannot assume roles yet. It needs permission to do so. Thus, we need to create a policy that enables this access and attach it to the user. We go and create a file called sts.json. Again, the name doesn't matter. And we write the policy that enables the user to assume the Terraform role. This is defined in the action part that grants the user STS assume role. STS stands for Security Token Service, in case you're wondering, and the resource defines which roles this user can assume. We only want this user to assume the Terraform role, so we just write the ARN of this role. Then we save the file. Now we need to attach this policy to the user. We can do this by running AWS IAM put user policy --username Terraform --policy name STS --policy document, and we supply the full path to the sts.json file that we have just created and stored in our current working directory. We are all set now. Let's double check that our user has enough permissions to log into AWS and also perform actions. So first we switch the profile to Terraform. Then we assume the Terraform role by running AWS STS assume role --role ARN. Then we paste the ARN of the Terraform role that we have just created. Optionally, we can supply a role session name. This is not really needed. We can call it AWS CLI-session. As you can see, the command responded with a set of new credentials. This is an AWS access key ID, an AWS security access key. Additionally, we have a security token with an expiry date. Let's copy all this somewhere so that we can use it later. Those are the credentials that the Terraform account can use to access AWS resources through the Terraform role. To use those credentials, we need to export them as environment variables as follows. Export AWS access key ID, and we paste the corresponding value from the notepad. Export AWS secret access key. Again, we paste the appropriate value from the notepad. Then the extra value, which is the token. Export AWS session token. Then we paste it from our saved text. You may be wondering now, if the Terraform user has two sets of credentials, the one saved under .aws/credentials, as we can see here, and the ones that we've just exported as environment variables. So which of those is the account going to use? Well, when we store AWS credentials in environment variables, they override the ones saved in file. Hence, the account will use the credentials saved in the environment variables. We can double check by running AWS STS get caller identity, which would return the name of the role currently assumed by our user. As you can see, we are using the Terraform role, and any AWS commands now will be issued through this role. For example, let's list the S3 buckets that we have. Remember, we tried running this command before and we were denied access. But this time, we are able to get a list of the S3 buckets that live in this account. When we run Terraform, we just need to run it using the Terraform profile that we've created earlier in this lecture. Then we will configure it to automatically assume the Terraform role when it starts accessing AWS resources. Terraform will automatically assume the role, retrieve the temporary AWS credentials including the session token, and use them behind the scenes. In other words, we won't need to run the sts assume role command that we've just ran, nor would we need to store the temporary credentials in environment variables like we did now. This was done just to show you how users with no permissions can assume roles that have the required policies attached to them. Now we are ready to use Terraform to create our infrastructure on AWS. Well, that brings us to the end of this lecture. Thanks for watching. Hello everyone. In this lecture, we start using Terraform to create the first part of our infrastructure, which is the VPC and the subnets. For an overview of the application and the target infrastructure that we are going to create in this section, please refer to the previous lectures of this section. The first thing we need to do is create the directory tree. Our application is called the weather app, so let's create a directory for that name. Inside that directory, let's create a subdirectory called infrastructure. This is where all our Terraform code will live. So let's get inside this directory and open our IDE. For this class, I'm using Visual Studio Code. You can use whichever IDE or code editor of your choice. Once we open Visual Studio Code, it is recommended that we install the Terraform extension since it will provide some code coloring and formatting. Let's create the files that will contain the Terraform code. We need a file called provider.tf, which will contain the cloud provider that we are going to use, which is AWS. It will also contain the name of the role that we are going to assume. Additionally, a file called main.tf, which will contain the actual code for building the infrastructure. We also need a file called variables.tf, which will contain the variables that we may need. There are several ways by which we can supply variables to Terraform when it runs. Perhaps the easiest one is to create a file called terraform.tf vars, which will hold the values for any input variables that we are going to use. So let's create that file too. Finally, a file called outputs.tf, which will hold any output values that our code will return. An important notice to make here before we move forward is that all those files are created by convention. That is, we are following best practices for file naming. But for example, we can place the output code in the main.tf file and Terraform will still run with no issues. But following convention helps keep our code base well organized and readable, especially if you are going to work in a team where other members will contribute to the code base. Our first file is provider.tf. We start with a Terraform stanza where we will be defining the providers that we are going to use. Notice that this is how Terraform can work with more than one cloud provider under the same code base. The required providers contain an AWS entry. The source of this provider is the official provider provided by HashiCorp. And the latest version at the time of this recording is 4.50. If we omit this part, Terraform will attempt to use the latest version at all times. This is not a good practice, since some newer provider versions may be incompatible with older ones, causing the code to break. So it's always advisable to explicitly define the version of provider you are using so that Terraform is restricted to using it. Notice that we are using this symbol which restricts Terraform to using the rightmost range of the version. So if a newer version of AWS provider is released and it's for example 4.51, Terraform will attempt to use it. The same goes for 4.52, 4.53 all the way to 4.59, but not 4.60, since this is out of the restricted range. This flexibility allows you to make use of newer versions with minor improvements that do not introduce breaking changes. Next, we need to configure the AWS provider to use the Terraform AWS profile and the Terraform role that we created in the previous lecture. So under the AWS provider stanza, we define the profile to be Terraform. This is much more secure than specifying the credentials of the Terraform user in clear text here. Anyone who wants to use Terraform needs to first obtain the credentials, save them in the local machine under a profile called Terraform, and Terraform will extract credentials from this profile at runtime. Remember from the previous lecture, the Terraform user does not have any permissions other than assuming the Terraform role. So let's instruct Terraform to assume the Terraform role by using the assume role instructions. We specify the role ARN. Optionally, we give a name to the session. And we are done with the provider file. Let's now move to the main file where we will define our VPC and subnets. To create a VPC, we use the AWS_VPC Terraform resource. At the minimum, it needs a CIDR block, which is the range of IP addresses that it can use. Let's make that a variable. So in the variables.tf file, we create a variable called CIDR block. The type of this variable is string. We can optionally define a default value for this variable so that it gets used when no value is supplied for this variable. But let's just not do that for now. Instead, let's define a value for that variable in the terraform.tf vars file. Our CIDR block of choice is 10.0.0.0/16. Now let's go back to the main.tf file and use this variable for the CIDR block. To access the value of a variable, you just need to use the var keyword followed by the variable name. Now we're ready to apply this configuration and create the VPC. Let's go to our terminal. The first thing we need to do, since this is the first time we run Terraform, is run Terraform init. What this command does is that it downloads any plugins or providers that Terraform is configured to use. In our case, it's the AWS cloud provider. Once we initialize Terraform, it's a good practice to run Terraform plan to see exactly what is going to be done for us in the infrastructure. So we run Terraform plan. Another best practice is to specify an output file for the plan. The advantage of this is that we can instruct Terraform to use this file to apply the configuration to the infrastructure. Otherwise, there is no guarantee that what's displayed in the plan is exactly what's going to be applied. So let's call our output file plan. As you can see, those are the AWS components that need to be created for us to have a working VPC. We're okay with that, so let's run Terraform apply followed by the name of the file that we used to save our plan, which was called plan. In a few seconds, Terraform returns with the results. The VPC was created. If we try to run the same Terraform plan command again, you would see that by comparing the saved state to the existing state on AWS, no more changes are needed. Recall from a previous lecture when we mentioned that Terraform is idempotent in the sense that it won't create duplicate components. The next thing we need to do is create these subnets. Remember, we need a total of 6 subnets, 3 of them private and the others are public. The important thing to note here is that we need the subnets to be spread among the availability zones. So instead of hard-coding the availability zones, we can just use Terraform data sources. A Terraform data source queries the cloud provider for components and returns the results. In our case, we need to dynamically determine the availability zones in the region that we will be working in, that is EU West 1, as defined in the Terraform AWS user profile. So let's create a data source of type AWS availability zones and call it available. We only need the availability zones that have the state of available. The result of this data source is a list that we can use with any resource that needs it. To create an AWS subnet using Terraform, we use the AWS subnet resource. Let's create the first private subnet. We call it private 1. We need to supply the VPC ID that this subnet belongs to. This can be brought from the VPC that we've created earlier in the file. We also need a CIDR block for this subnet, that is, the range of IP addresses that this subnet can use. Obviously, this should be a subset of the parent CIDR range used by the VPC. So let's use a variable here so that we can change it from one environment to another. In the variables, the TF file, we define a variable for the first private subnet. The type is string. Since we have 2 more private subnets and 3 more public ones, let's define their CIDR variables here as well. So we just copy and paste the private subnet and just change the name and the corresponding parameters. We are going to do this for the 2 private subnets that we have and also for the 3 public subnets. Now that we have the variables defined, we need to supply values for them. So let's pay a visit to the terraform.tfvars file and add the following. We want to keep things simple so that CIDR blocks will be of type C, which allows us to have up to 254 IP addresses in the subnet. This is more than enough for the purposes of this lab. So we specify the CIDR range of the first private subnet, the second, and the third. In the same fashion, we define the CIDR ranges for the 3 public subnets that we will create. Now that we have the CIDR ranges and the availability zones ready, let's continue with the subnet creation. So back to the main.tf file, we extract the CIDR range from the appropriate variable. The next parameter we need to define is the availability zone where this subnet will live. We can use the list of availability zones returned by the data sources as follows: data.aws_availability zones.available.names and between square brackets 0, where 0 here refers to the first item in the list, since it is 0-based. If you are using the same region that I'm using, then this one should translate to EU West 1A. This is all what we need to create the first private subnet. The other 2 subnets are just replicas of this one. We just need to change the subnet name, CIDR range, and availability zone. Once we're done with the private subnets, we can still copy the code and use it to create the 3 public subnets. At this point, there is no difference between the private and public subnets. The difference will become evident when we create the routing table later on. For now, we just need to make sure that each availability zone contains 2 subnets, one private and another public. The next component we need to create is the Internet Gateway. If you recall from a previous lecture when we discussed the infrastructure architecture, the Internet Gateway will be used by the public subnets so that they are reachable from the public Internet. To create an Internet Gateway, we use the AWS Internet Gateway resource. We only need the VPC ID here, which we can get from the VPC resource that we've defined. Now we need to create the NAT Gateway, which would be used by private subnets to access the Internet. The NAT Gateway needs an elastic IP address to be allocated first. An elastic IP is just a static IP address that is provided by AWS. To create one, we use the AWS EIP resource. We can call it NAT-GW to denote that this is created specifically for the NAT Gateway resource. Once we have that, we can start creating the NAT Gateway itself by using the AWS NAT Gateway resource. The allocation ID is the ID of the elastic IP address that we've just created. The NAT Gateway needs a public subnet to live in. We can use one of the public subnets that we already have. Some setups opt to create a separate NAT Gateway per availability zone. That is, one NAT Gateway per each of our public subnets, or in other words, 3 NAT Gateways. But for this lab, we are only creating one NAT Gateway, and it will be hosted in the first public subnet. To make sure that the order of component setup is correct, we need to create the Internet Gateway first before creating the NAT Gateway, since it depends on it. Terraform allows us to define dependencies by using the dependOn keyword. It takes a list of resources. In our case, we are only dependent on the existence of the Internet Gateway, so let's add that. Now we have 6 subnets, an Internet Gateway and a NAT Gateway. It's time to assign subnets to each of them. As we've mentioned before, the Internet Gateway or the NAT Gateway is what defines whether a subnet is public or private. To do that, we need to create a routing table for the public subnets. We use the AWS route table resource for that. It needs a VPC ID, so we specify the ID of the VPC that we've created earlier. We can also add a route entry to the route table. We specify that any IP address that is not within the CIDR range of the VPC should be routed through the Internet Gateway. To do that, we specify a special CIDR block which is 0.0.0.0/0 and define the gateway ID as the Internet Gateway ID. Similarly, we define the routing table for the private subnets. It looks exactly the same except that we use the NAT Gateway keyword and specify the ID of the NAT Gateway that we've just created. Now we have 2 routing tables, one for the private subnets and another for the public ones. We only need to attach the Internet Gateway to the public subnets and the NAT Gateway to the private ones. We do that by using the AWS route table association resource. We need an association for each subnet. So for the private subnets, we create an association that just hooks the subnet ID with the route table ID. We can do the same thing for the rest of the subnets. Just make sure that the private subnets are associated with the private routing table, while the public ones are associated with the public routing table. Once we are done, we make sure that all our files are saved. And we go to the terminal and run the same Terraform command again. Terraform plan to see what Terraform will do for us. Again, as a best practice, we save the plan to a file to guarantee execution. If we are okay with that plan, we can run Terraform apply plan, where plan is the name of the file. Terraform is creating the VPC, subnets, route tables, Internet Gateway, and NAT Gateway resources. It might take a minute or two to complete since the NAT Gateway takes considerably more time to get deployed. I am going to speed up the video here to save the lecture time. Once we're done, we can view the components that were created for us in the AWS console just to make sure that Terraform did what it was asked it to do. So, logging in to AWS, we go to the VPC part, As you can see, we have two VPCs, the default one that gets created in every region for every account, and the VPC that we've created by Terraform. We can also have a look at the subnets. We can see that we have 6 subnets with the designated CIDR ranges. We also have an internet gateway and a NAT gateway. For the route tables, we have 2. One of them directs non-VPC traffic to the internet gateway, and the other directs it to the NAT gateway so that we can have public and private subnets. So, in this lecture, we demonstrated how we can use Terraform to create the basis of the first environment in our class, where we are going to use plain EC2 instances to host our application. That brings us to the end of this lecture. Thanks for watching. Hello everyone. In the previous lecture, we saw how we could use Terraform to create our VPC, subnets, and the necessary components that allow subnets to be public or private. However, if you notice, when we attempted to run Terraform for the second time, it didn't create a second VPC. Instead, it informed us that there are no differences between the running infrastructure and the code that we have, and thus there is nothing it can do. This might be a good thing when we don't need to duplicate our components each time we run Terraform. But sometimes we do want to duplicate our components. Maybe we need a second VPC with 6 other subnets for testing purposes. That second VPC needs to have the exact same configuration except for the IP ranges. To do that with our current setup, we need to create a duplicate of our existing infrastructure folder, which contains the code for creating the VPC, but in another directory, and run Terraform from within that directory. But that solution violates the dry or do not repeat yourself design principle. Whenever we need to make a change to the code, for example, create a NAT gateway per availability zone instead of just one, we need to apply that change to all the directories that create the VPC. Instead, Terraform offers a much better approach. We can use Terraform modules. A module encapsulates the code in a reusable unit. We can call modules from other Terraform files, pass values to their variables, and use their outputs as inputs to other modules. But let's not get ahead of ourselves. Let's see how we can refactor our project to store the VPC code in a separate module of its own. First, we need to destroy the existing environment. This can be done by running Terraform destroy inside the infrastructure directory. Terraform examines the list of actions that it needs to do and prompts you for an approval by typing yes. So let's do that. In a few moments, the VPC, the subnets, the internet gateway, and all the other components that we created in the previous lecture are terminated. Notice the ease of infrastructure management now. With just one command, you are able to track and terminate all the components that you don't want to use. Compare this to having to manually maintain a list or a spreadsheet with the names or IDs of the infrastructure parts. Alright, so let's now refactor our code to create a module for that VPC. The first thing we need to do is create a directory that will hold all the modules, since we may be creating more than one. We call this directory modules. Underneath it, we create a directory that will hold our VPC code, and we call it VPC. Then we just need to move the Terraform files that were used to create the VPC and the rest of the infrastructure under the modules/VPC directory. We are moving the main, variables, and outputs files only. The Terraform.tf vars will not be moved for now. We'll deal with it in a few moments. In the infrastructure directory, we create a new file called main.tf. This file will act as the bootstrapper that will call and manage all of our modules. In this file, we start calling our VPC module by typing module VPC. Notice that the name we chose to call the module with does not necessarily have to be the name of the directory that holds the module. But it's considered a best practice to have the same name for the modules directory and how you call it in the code to avoid confusion. The module needs to know where to find its files. This is where we specify the source directive. We need to type the relative path to the module, and notice here that we need to start the path with a dot, which indicates the current working directory. So, starting with the current directory, we descend to the modules directory, then the VPC subdirectory. This is where our module lives. But the code that we used in the previous lecture uses variables and it needs values for those variables. The module accepts those values the same way we specified them in the Terraform.tf vars files. So, we just copy all the values from the Terraform.tf vars directory and place them underneath the source directive, like so. As we mentioned earlier, there is more than one way to feed values to Terraform. This is just one of them. I personally prefer to put the values for the variables in the module file so that we can have a clear view of what each module is using. we can delete the terraform.tfvars file since it won't be needed any longer. Now let's try our new setup and see if it works or not. We need to run Terraform init again since we are using a module. Whenever a new module is added to the code base, we need to run Terraform init. Then we run Terraform plan-out plan as we're used to. Okay, seems that we have a file that was misplaced. It's the variables file, so let's add it underneath the modules/VPC directory as it should. Now, as you can see, we have a very similar plan to the one that we had when using the last lecture's code. If we are happy with this, we can run Terraform apply plan. In a few moments, we'll have everything up and running again. I'm going to speed up the video so that we don't have to wait for the entirety of the operation. And we're done. If we have a look at the AWS console, we can see that we have our VPC and subnets back together with the other components. Now let's see the advantage of using modules. If we go back to the main.tf file, we can duplicate the module code to create a new VPC. Let's say VPC2. Obviously, we will also need to change the input values here, like the CIDR ranges, but since we are not genuinely interested in creating a second VPC, let's just leave the values as is. And move to the terminal. We need to run Terraform init again, since we've added a second module to the file. Then we can run Terraform plan, and we don't need to save the output to a file since we are not intending to create a VPC. As you can see, Terraform is going to create a second VPC under our AWS account instead of telling us that no changes have been detected between the code and the running infrastructure. Compare this to the output that we've seen when we were not using modules in the previous lecture. One final thing we need to visit before closing this lecture. We've not used the outputs file till this moment. We mentioned before that the outputs file is used to place any values that Terraform will return once it is done. So let's go to the outputs file in the module, and let's say that we want our module to return the VPC ID. The VPC ID is one of the most used parameters. Any modules that rely on the VPC must have the VPC ID. So in the outputs file, we add output and specify the name of the output value that we are going to return. Then we define the value, which is the resource type, followed by the name, which is main, then the value we need to return, which is the ID. Now we can retrieve this value from the module when it runs. But to do that, we need to instruct Terraform as to where we need that value returned. Let's move back to the main.tf file where the module is called, and let's add the output directive. Since we are calling the module from a file, any Terraform output should be defined in this file. We can name this output also VPC ID, although we can give it any other name, but let's be consistent to avoid any confusion. Then the value needs to be retrieved from the module rather than the resource since we don't have access to the resource. We can only reach the module at this point. The module name is VPC and the output of that module is VPC ID. Now if you go to the terminal, we need to run Terraform init since we've removed a module from the code. To determine the VPC ID, we don't need to run Terraform apply again. Instead, we can just run Terraform refresh. What this command does is that it checks the current state of the infrastructure against the code and returns any output that was defined in the code. As we can see, we have the VPC ID returned. So, in this lecture, we refactored our code to use Terraform modules. We also discussed the advantages of using modules over using plain Terraform code. Finally, we saw how we could use outputs to return important information about the provisioned infrastructure components. That brings us to the end of this lecture. Thanks for watching. Hello everyone. In the previous lectures, we saw how we could set up an AWS VPC together with the subnets and the required components using Terraform. We also have the advantage of using modules so that we can reuse our code to duplicate infrastructure components in the same environment or create new environments without having to copy and paste our code. In this lecture, we will demonstrate an even cooler feature that Terraform provides, which is the ability to use modules that are stored remotely. To understand this feature, let's have a look at our current code base. We have a directory called modules that we can call from anywhere in our system. We just need to specify the path to the module that we need. But what if another project wants to use our code? Or what if we want to share it with the open source community? Terraform allows you to use modules that are not stored locally on the file system. If we visit the official documentation, we can see that we can use Terraform registry, GitHub, Bitbucket, other Git repositories like GitLab, a web server, an S3 bucket, a GCS bucket, in addition to other options. As you can see, we are not limited when it comes to hosting our module anywhere on the web. So, let's start by exploring the option of storing our VPC module in a separate Git repository on GitLab. The advantage of this method is that you are decoupling the module code from the environment-specific implementation. Several teams can contribute to the module code without having to deal with the actual infrastructure that will be using this module. You can also share it with other teams or the open source community, as we've just mentioned, and have the benefit of a developer collaboration from around the globe. For this demo, I will be using GitLab as my Git repository of choice, but you can use Bitbucket, GitHub, or whichever service you like. So, I shall navigate to gitlab.com, log into my account. You can create a free GitLab account if you want to. And I'm going to create a new project that will host my Terraform modules. We need a descriptive name, so let's call it Terraform modules. I will not initialize it with a README file. I just want an empty repo. Once it is created, let's go to the terminal. And before we move any further, we need to destroy the existing environment since we will be refactoring our code again. So inside the infrastructure directory, we run terraform destroy. When prompted, we answer yes to confirm our decision. Once we terminate the environment, let's work on our new repository. Make sure you are outside the weather app directory since this will be a separate and independent code base. Then let's clone this empty repository to our local machine and get inside the directory that got created for us. Then we need to place our VPC code inside this directory. So let's move it from the weather app infrastructure directory and put it here. Once we do, we need to use Git to add the newly created files to the staging area. Then we commit and supply a message. Let's say adds the VPC module. Finally, we push our code to the remote repository by running git push -u origin main. Our VPC module is now not stored locally but in a remote Git repository. Hence, we need to modify our main.tf file to point the module source to the repository instead of the local path. To do this, we use the following format: git followed by double colons, then /git @gitlab.com/abohamid, which is my username on GitLab, /terraform modules, which is the repository name, .git. But the VPC module code does not live in the root of the repository. It is rather contained under a directory called VPC. We store each module in a separate directory so that we can use the same repository for storing multiple modules. To indicate that the code we need is located under a subdirectory, we use double slashes after the repository name, then we mention that directory name, which is VPC. Notice that this is how we can connect with a generic Git repository. Terraform supports connecting to GitHub and Bitbucket using an alternative syntax. You can refer to the official documentation for connecting with your remote location of choice. Optionally, we can also specify a release name, a branch name, or even a commit hash to indicate which version of the code we want to use. We do that by adding a question mark followed by ref equals, then the string that indicates the code version. Although this is an optional step, it is highly recommended that we specify a code version. This becomes of special importance when several teams contribute to the same module. You need to maintain the version that is consistent with the Terraform version. Otherwise, you may encounter unexpected compatibility issues between the module and Terraform. Having said that, we don't really have a release version for the VPC code that we've just pushed. But to emphasize the concept, we can just use the branch name, which is main. The rest of the file can remain the same since our module has not changed. It still accepts the same input parameters and returns the output values. Let's test our changes and make sure it works. We need to make sure we are back in the infrastructure directory. Since we changed the module location, we need to reinitialize Terraform, so we run terraform init. Notice that Terraform init this time downloads the module code from whichever remote location you specify and stores it locally on the file system so that it can be used. Thus, you need to make sure that Terraform is able to connect to GitLab or the remote location that you chose, authenticate with valid credentials, and download the code. In our case, I'm using the SSH authentication method to connect to GitLab and download the code. Once the initialization is complete, we can run Terraform plan to make sure that Terraform will recreate the same environment that we had before in the last lecture. As we can see, we have all our components ready to be provisioned again. However, we are not going to save this plan to a file because we are not going to apply it. Instead, let's discuss an even more robust method of deploying a VPC together with the subnets and the necessary components. Earlier in this lecture, we mentioned that Terraform can use modules stored in remote locations. Perhaps the most well-known place where you can find plenty of well-crafted, production-ready modules is the Terraform registry. We can reach it by going to registry.terraform.io. and search for a module keyword. In our case, we want a module that can build and deploy an AWS VPC. So let's enter VPC as the keyword, select AWS as our provider. We have several modules, all of which can deploy a VPC and its child components. Let's pick the first one. Each module stored in the Terraform registry comes with detailed instructions on how to use it, which parameters it accepts as inputs, and which values it returns. So if we have a look here, we can see that the module is designed to accept the availability zones as a list instead of using a data source to automatically get them. It also accepts the private and public subnets as a list instead of supplying each in its own variable. If we go a little further down, we can see that by default the module is going to create a NAT gateway per availability zone. That is, 3 NAT gateways. Obviously, this helps with high availability, but for our demo purposes, we don't need to multiply the cost of running a NAT gateway by 3. Instead, we need to instruct the module to create only a single NAT gateway in the VPC. To do that, we set the enable NAT gateway to true, the single NAT gateway to true, and 1 NAT gateway per AZ to false. Armed with this information, let's head back to our main.tf file. We start by changing the module source. Instead of using the module that we pushed to the repository, we want to use the one from the Terraform registry. Terraform accepts a special syntax for using modules stored in its registry. We just copy the path from the module's documentation and write it here. Again, specifying the version of the module is not required, but is highly recommended. Ignoring to mention a specific module version instructs Terraform to always use the latest version, which may introduce breaking changes. The latest version of this module at the time of this recording is 3.19.0. Now, let's define the AZs as the module requires. We need the 3 availability zones of the EU West 1 region. Then, we specify the public and private subnets in 2 lists with the CIDR ranges that we've selected. For a change, let's reconfigure the CIDR ranges for the public subnets to be over 100 since we will be using this VPC for the rest of the class. Finally, we supply the necessary parameters that instruct the module to deploy a single NAT gateway. In the module that we used in the previous lecture, we had an output parameter that returned the VPC ID once the VPC was created. But since this is a different module with separate code, we need to review the type of outputs this module returns. So we go back to the module page and scroll down till the end. We can see that we have a table that mentions several output parameters that this module provides. All what we need to do to have one or more output parameters is to specify its name in the outputs part of the main.tf file. We can see that this module already has an output parameter called VPC ID. Going back to the main.tf file, we can see that we already use the same name. Thus, we don't need to change anything. The code will return the VPC ID the same way as when we use our own module. Now, let's test our work. We go to the terminal, and we run Terraform init. Again, this command will attempt to download the module code from the Git repository where it is hosted and store it locally on the file system. Then we run Terraform plan-out plan to create and store the plan to a file. Finally, we use Terraform applied plan to provision the infrastructure using the plan file that we've just created. As usual, I'm going to speed up the video to save the lecture time. Once we're done, we can go to the AWS console using the browser and have a look at what the module has created for us. We have a VPC, 6 subnets, the relevant route tables, the Internet Gateway and the NAT Gateway, so our module created the infrastructure that we needed. As a rule of thumb, whenever you need to provision infrastructure components through Terraform, you are advised to search the registry first for any ready-made modules that achieve the required result. Those modules have been time-tested, they are used by many projects around the world in production scenarios. This means that any real-world bugs are discovered and addressed as soon as possible. If the functionality that you are after is not available through a ready-made module, or if the module is not customizable enough, you can go ahead and create your own. Placing modules in separate repositories is also a good practice since it allows you to decouple the module code from the environment code. This allows you to create abstract, highly customizable modules that can be used with any type of project. Well, that brings us to the end of this lecture. Thanks for watching. Hello everyone. So far in this class, we've been using Terraform to provision and manage infrastructure components for us. We mentioned several times that Terraform is idempotent in the sense that it will not duplicate existing components using the same code base. But we never mentioned how Terraform knows which components it has already created in the previous run so that it doesn't attempt to recreate them. Whenever Terraform works, it uses a file called the state file. The sole purpose of this file is to record the actions that Terraform performs. For example, when we created the VPC and the subnets, the state file already has a record of the VPC, the subnets, and all the other components that were created in the process. The state file uniquely identifies those components so that they cannot be duplicated. By default, Terraform stores its state in a file called terraform.tf_state that is located in the same directory where Terraform runs. However, keeping the state file on your local machine suffers several drawbacks. For example, if you use another machine like a different laptop, Terraform cannot determine which components it has already created. The result is that it may attempt to recreate existing components, which may cause all types of mess. If this file got accidentally deleted, you lose the state forever. Other team members need to ask you for the file before they can work on the same infrastructure as you. Whenever anyone wants to work on the project, they need to ask the last person who used Terraform to provide the state file to be consistent. Obviously, this is counterproductive. For those reasons, Terraform offers several ways to store the state file in a remote location. For example, an AWS S3 bucket, Azure Blob Storage, Google Cloud Storage, Console Key Value Store, and even a Kubernetes cluster, to name a few. The way Terraform stores the state file is called backend configuration. In this class, we are going to use an S3 bucket as a backend storage method. As a best practice, we enable bucket versioning. With versioning, we protect the state file from deletion. Additionally, when the state file gets corrupted for whatever reason, we can retrieve a previous working version. Once we have a central location for storing Terraform state, this means that more than one user can invoke Terraform. By nature, IAC tools cannot be used concurrently. The tool should have exclusive access to the infrastructure that it manages. Otherwise, if more than one Terraform session is running at the same time, they may overwrite each other, causing unexpected results. For that reason, Terraform uses a lock file so that only one user can run Terraform against the environment at any given time. Again, by default, the lock file lives in the local machine from where Terraform is run. And again, as a best practice, we need to use a central location that is globally accessible. Since AWS is our cloud provider of choice, we will use a DynamoDB table for storing the lock record. If you're not familiar with DynamoDB, it's a NoSQL database that is managed by AWS. So, now that we know what needs to be done, let's get into action. The first thing we need to do is create an S3 bucket. We run AWS S3 API create bucket. The bucket name needs to be unique among AWS. Let's name it Modern DevOps Terraform State. We need to create this bucket in the EU West 1 region instead of the default one, which is US East 1. But to do that, we also need to apply a specific bucket configuration where the location constraint is set to EU West 1. As we've mentioned a few moments ago, the bucket needs to support versioning. To do that, we run AWS S3 API put bucket versioning --bucket modern DevOps Terraform state --versioning configuration status equals enabled. So now the bucket is ready for use. Now let's create the DynamoDB table by running AWS DynamoDB create table -- table name. We can call it Terraform backend lock. Then we need to set the attribute definitions. You can think of attributes as columns of an SQL database. We only need one attribute that Terraform will use. It's called lock ID. The attribute type is S or string. The key schema attribute name acts as the primary key in a SQL database. The attribute is the lock ID and its type is hash. Finally, we need to set the provision throughput for this table. We set the read capacity to 5 reads per second and the write capacity also to 5 writes per second. This is more than enough for Terraform locking. In a few seconds, the table is ready for use. Now we have the S3 bucket and the DynamoDB ready. We need to instruct Terraform to start using them. So in the provider.tf file, we add a backend stanza. We set the backend type to S3. The bucket name is modern DevOps Terraform state. And the key, which is the name of the file that Terraform will use for storing the state, is Terraform state. The name doesn't really matter here. The region where the bucket lives is EU West 1, and the DynamoDB table for locking is Terraform backend lock. Now we already have an infrastructure up and running. We don't need to destroy and recreate this environment. Instead, we can migrate the state from the local file to the S3 bucket. To do that, we run Terraform init -migrate -state. Terraform will automatically write the current state to the S3 bucket. And from this point further, the bucket will be used for persisting state. Let's double check that Terraform will use the state stored in the S3 bucket, so we run Terraform plan. And as you can see, it detected that no changes are needed, which means that it was able to read the state from the bucket and compare it to the existing running infrastructure. So, in this lecture we discussed how Terraform manages the backend configuration, which is also referred to as the state management. We were able to use centralized storage for the state as well as the locking mechanism. Now we can use Terraform from anywhere and not necessarily from our local machine. That brings us to the end of this lecture. Thanks for watching. Hello everyone and welcome back. In the previous lectures, we laid the necessary grounds for our virtual machines. We created the VPC, the subnets, the necessary route tables that designate private and public subnets for the different use cases that we have. In this video, we are going to create the virtual machines that will serve the content of our application. In AWS, virtual machines are referred to as EC2 instances. EC2 is short for Elastic Compute Cloud. Now, before we open our IDE and start coding, it's a good idea to have a second look at the application diagram to see exactly what we need to accomplish here. For a quick recap, the Weather app is an application where you can enter the city name of your choice and the application instantly brings the current weather conditions for this city. Before you can do that, you need to sign up by choosing a username and password, then use them to log into the application. The application is made up of 3 services. The first one is the authentication service, which is responsible for accepting and storing the credentials for new users when they sign up. It listens on port 8080 and receives the data from the UI service. It also checks whether users have valid credentials to log in or not. If the credentials are correct, it sends a token to the UI service, which in turn sends it to the user's browser. This token is how the user can log in again without having to resupply their credentials. The auth service stores the data in a MySQL database. The UI service is in charge of displaying all the web pages to the users. It communicates with the auth service for users' sign-up and authentication. Last service we have is the weather service. It is responsible for getting the weather data from an external weather API service that is hosted by a third-party application. It gets the city name from the UI service and responds back to it with the weather information that it got. To deploy this stack on AWS, one way of doing this is using EC2 instances. So we have a VPC with 3 public and 3 private subnets. We create one instance per application service and place it in one of the private subnets. Only the UI service is exposed to the end users. It is reachable through an application load balancer. We also need an RDS instance for a MySQL database, a parameter store, and a secrets manager for storing the sensitive and non-sensitive parameters that our application may use. So, in this lecture, we are going to create 3 EC2 instances for our 3 services. We are also going to create a Bastion server, also referred to as the jump server. It is used as a tunnel to reach our EC2 instances that are in the private subnets. The Bastion server obviously needs to be located in one of the public subnets so that end users can reach it. I guess by now we have a firm understanding of what we are up to. At any point, you can refer to this lecture or the ones titled Getting to Know the Application and Getting to Know the Infrastructure whenever you feel lost or you don't understand why we are doing certain things in a certain way. Now, let's head to Visual Studio Code and have a look at the main.tf file. So far, it only contains the VPC module which we got from the Terraform registry. Some of the parameters used in this module will be needed further down the file. It makes a lot of sense to put those values in a global area where other modules can also make use of it. Terraform offers the locals part where we can define variables together with their values and use them anywhere within the current scope. Our current scope now is the main.tf file, so any module defined here can reach any value defined in the locals part. We need to have the CIDR block, the availability zones, the public and private subnets. So in the VPC module, we need to replace the hard-coded values that we have there with the ones defined in the locals part. We can do this by simply prefixing the variable's name with a local keyword. Next, we need to start creating the EC2 instances. As a prerequisite, we need to first define the security groups that will get associated with the instances that we are yet to create. We need one security group per service, that's 3 security groups in total. We also need a 4th one for allowing SSH access to the instance. As we're used to, whenever we need to create a component using Terraform, it's always a good idea to search for the existence of ready-made modules in the registry and pick one if appropriate. So we visit the Terraform registry and search for security group. We have the results, let's pick the first one. By the way, all the modules that we've been using so far belong to the same repository. This is one of the most used Terraform modules. If we have a look at the documentation and the examples, we can see that we have the module source and the version. We also have a brief example about how this module can be used. So let's head back to the IDE and start coding the module. The first security group that we need to create is the one that would be used by the authentication service. So we name the module auth service SG, which should be descriptive enough. The source is the one mentioned in the docs, Terraform AWS modules /security group /AWS. Again, and as a best practice, we need to mention the version of the module that we are using. This is also copied from the docs page. The name is auth service. The description is not really important, but let's say the security group for the auth service. The module needs the ID of the VPC where this security group will live, so we refer to the VPC ID that was returned from the VPC module defined earlier in the file. Next, there are several ways by which we can instruct the module about which ports we need to open, which is the source, the protocol, and so on. For a quick recap, security groups act like firewalls to the EC2 instances. They control which traffic should reach or leave the instance. It accepts a source port, a destination port, a protocol, and a CIDR block for each of the incoming and outgoing connections. So for this lab, we are going to use ingress with CIDR blocks as an input parameter. It accepts a list of objects. We only need one object for the auth service since we only need one port to be open. So the from port is 8080, the to port is also 8080 where the auth service listens. The protocol is TCP. The description can be something like auth service ports. Finally, the CIDR blocks, which define the IP range that this security group will allow connections from, is the CIDR block that we defined in the locals part of this file. We also need an egress block. Ingress refers to incoming connections, while egress refers to outgoing ones. Again, we use egress with CIDR blocks to be consistent. Here, we are allowing all traffic on any port and any protocol. In more controlled environments, you may want to also restrict which ports the EC2 instance is allowed to talk to. But for this lab and in most real-world scenarios, we can just get away with allowing the instance to talk to all ports. So, the from port is 0, the to port is also 0, the protocol is -1, denoting any protocol type. The description could go as allow all outbound connections. The CIDR blocks can also be the VPC CIDR block. We can treat this security module as a template for defining the 3 other ones. All we need to do is duplicate the module code. Then make the appropriate changes to the code starting with the name. This security group will serve the UI service, so the name in all the occurrences should be UI. The port should also change to reflect the port where the UI service would listen, which is 3000. Everything else stays the same. Let's do the very same thing with the weather security group. Again, we change the name where we find it. and the port should be 5000 where the weather service would listen. Our final security group is the SSH one. This oversees allowing SSH connections to the instances. We could have added port 22, which is the SSH port, to each of the preceding security groups, and it would achieve the same result. But I wanted to demonstrate how a single instance can be associated with more than one security group at a time. So again, we paste the skeleton code for the security group. We change the name to be SSH-SG, and the security group name is the SSH service. The description can be read as security group for SSH access. The from port here is 22, which is the standard SSH port. The to port is the same. But the CIDR block here needs not be restricted to the CIDR block of the VPC, since the Bastion server is also going to use this security group. So we need to set this parameter to 0.0.0.0/0, which denotes any IP range. Don't worry, still, no one from the public internet can access any machine in the private subnet over SSH, even if the security group allows it. The reason is that they are not associated with any internet gateway, which means that connections from the public internet will not even reach the security group to start with. Now that we have 4 security groups defined, before going any further, let's see what Terraform will build for us given this new code. In the terminal, we need to run Terraform init since we introduced new modules. Once Terraform is initialized, we can run Terraform plan-out plan to get an overview of what will be done for us. If we are happy with that, we can run Terraform apply plan to apply the instructions that we have saved in the plan file. In a few seconds, Terraform completes. Let's go to the AWS console and have a look at the security groups that we have now. So we type security group in the search box. Security groups are part of the EC2 service and not a service of their own. As you can see, we have 4 security groups created for us. Examining the details of each one of them, we can see that we have the correct ports and CIDR block as we desire. Okay, so now we have the security group ready. Let's move to the second prerequisite that we need for creating our EC2 instances, that is the key pair. An SSH key pair consists of a public and private key. It is used for logging into the remote machine without having to supply a password. To create a key pair on AWS and associate it with the EC2 instances that we are yet to create, we need to have a private and public SSH keys. You can do that on Linux, Mac OS, or Windows Subsystem for Linux, aka WSL, by just running SSH keygen and following the prompts. On Windows 10 or later, if you are not using WSL, you can either use the OpenSSH client or an SSH tool like PuTTY. In the resources part of this lecture, I will place a document that details how you can do that. Regardless of which OS you are using or which tool you invoked, you will end up having 2 files. They are typically called id_rsa and id_rsa.pub. The first one is the private key. This should be treated like a password. It should only be viewed by you, and it should not be shared with anyone. The second file, however, is the public key. You can safely share it with other people. When you need to authenticate to a remote machine using SSH keys, you place the public key on the remote machine, while the private key stays on your laptop. Terraform can do that automatically for us by creating a key pair on AWS that contains our public key. Later on, AWS will inject this public key to any EC2 instance that uses this key pair. The result is that you can use the private key to log into any EC2 instance that we create. So, for all this to happen, we need to copy the contents of the public key to the clipboard. Then, in the main.tf file, we need to create a resource called AWS key pair. We can call it DevOps. Notice that we are not using a module here, since this component is so simple that creating a module just for it is over-engineering. The resource just needs the key name on AWS. We can call it DevOps key. Then, the public key. We can just paste the content that we've just copied a few seconds ago. It's perfectly fine to store the public key in Terraform and commit it to version control. Again, let's see what Terraform will create for us by running Terraform plan-out plan. Notice how we didn't run Terraform init since we didn't add any new modules. As you can see, the plan is to create a key pair, so let's just do that. Terraform apply plan. It takes only a few seconds to complete. Now let's have a second look at AWS and see the key pair. Again, it is part of the EC2 dashboard, so we just click on the key pairs from the left navigation bar. And sure enough, we have our key pair created. We can only see the fingerprint of the key, but not the actual public key itself. Now, both prerequisites are available for creating the EC2 instances, the security groups, and the key pair. It's time to figure out the best way to create EC2 instances using Terraform. Again, we search the Terraform registry for the existence of a module that can do that for us. We can see that we have an EC2 module. Let's click on that. It too belongs to the same repository whose modules we use to create the VPC and the security groups. Having a quick look at the documentation and the examples, we can see that it can be used to create a single or multiple EC2 instances. It can also be used to create spot instances, but we are not going to use that for now. Going back to the code, let's add a new module and call it auth EC2 instance, since it will be responsible for creating the EC2 instance of the authentication service. The source is Terraform AWS module /EC2 instances /AWS. And don't forget to add the version. The instance name is auth instance, which is descriptive enough. The next parameter we need is the AMI ID. In AWS, the AMI stands for AWS Machine Image. It is a pre-baked virtual machine that contains all what's needed to have a working operating system with some essential tools instead of having to install everything from scratch. In other words, the AMI saves you the time and effort of installing the operating system, creating a user, and deploying a minimal working environment. Instead, it provisions that for you so that you can start working as soon as you deploy the EC2 instance. For this lab, we are going to use Ubuntu as the operating system of choice for all the instances that we will be creating. We can easily get the AMI ID for Ubuntu by going to cloudimages.ubuntu.com/locator/ec2. This is a website that lists all the available AMIs for Ubuntu for different versions and architectures. We go to the end of the page where we can apply filters. AMI ID varies by region, so we need to select the current region, which is EU West 1. We also need to select the version of the operating system. Let's pick the latest LTS or long-term support version. Finally, we need to pick the one suitable for our architecture. For this lab, we are using x86 architecture, so we copy the AMI ID of this architecture type. We go back to the code and place this ID in the locals part of the file, since several modules are going to make use of it. Then in the EC2 module, we define the AMI and point it to the one in the locals. We also need to specify the instance type. We are going to use the T3 micro instance since it would fit our needs and won't cost a lot. Let's define the instance type in the locals part again. And refer to it from the module when specifying the instance type. The key name is the DevOps key that we've created a few moments ago. Do we need to enable AWS monitoring for this instance? Yeah, why not? Now comes the part where we specify the security groups that would be associated with this instance. We use the VPC security group module IDs module variable. It accepts a list so that we can associate more than one security group with the instance. We specify the auth service security group ID, which can be easily brought from the outputs returned from the auth service SG module. We also need to allow SSH access to this instance, so we add the SSH SG service security group ID to the list, again by getting the value returned from the SSH SG security group module. Finally, we need to get the subnet ID where this EC2 instance will live. We already have 3 private subnets. Let's use the first one of them. The private subnet IDs are among the output values of the VPC module in a list. What we need is to pick the first one. In Terraform, we can use the element function. It takes a list as its first argument, so we specify module.vpc.privateSubnets. The second argument is the index of the element you want to return from the list. Since it is zero-based, the first element is denoted by 0. The return value of this function is the subnet ID of the first private subnet that we have. And that's all what we need to create an EC2 instance for the auth service. Before going any further, let's see how far this module can get us. In the terminal, we run Terraform init since we are introducing a new module. Then we can run Terraform plan-out plan as usual. Then we follow this by Terraform apply plan. The operation may take a few seconds up to 1 minute. I will just speed up the video to save the lecture time. Once done, let's go to the AWS console and see what has been created for us. Going to the instances part of the EC2 dashboard, we can see that we have a virtual machine created for us. Examining the details of this instance, we can see that it has the properties that we defined in the code. It is also associated with the correct security groups so that suitable ports are open. That's nice. Let's replicate the same module to other EC2 instances. So in the code, we copy the module code and paste it again. We need to change the name in all the occurrences from auth to UI. This includes changing the appropriate security group to point to the one created for the UI service. Finally, we need to change the subnet ID to point to the second private subnet. In a very similar fashion, we paste the module code again for our third service, which is the weather. And again, we need to change the name where it appears. And the subnet ID needs to go to the third private subnet in our list. It's worth noting here that putting each EC2 instance in a separate subnet is only meant to show how we can do that using the EC2 module. However, it is by no means a way of achieving high availability or fault tolerance. We're not providing those at this part of the lab, but we will be doing that later in this class. Now, next comes our Bastion server, which is also referred to as the jump server. We change the names as appropriate, but in the security groups part, we are not interested in any other group other than the SSH one. That's because the only purpose of having a Bastion server is tunneling SSH connections from the public internet to the private subnets. Accordingly, the Bastion server needs only accept SSH connections on port 22. Finally, we can place the instance in the first public subnet that we have so that it accepts connections from the outside world. Now let's move to our terminal, run Terraform init since we have a number of new modules introduced. Then we run Terraform plan-out plan to create a plan of what Terraform needs to do and save it in a file that we can use later. Once we are okay with what Terraform is going to do, we can run Terraform apply plan. Since we are provisioning more than one EC2 instance this time, the operation may take a little longer. As soon as it's done, we can go to the AWS console and see what was created for us. As you can see, we have all our servers created with the details that we've specified in the code. But if we look at the Bastion server, we can see that there's something wrong with it. It doesn't have a public IP address, which means that it won't be reachable from the outside internet. Why is that? Now we can spot it. The Bastion server was created in a private subnet where it should be placed in a public one instead. It must have been a bug in our code. So let's go back to our IDE. And indeed, we need to change this part to point to the first public subnet instead of the private one. Now, this is a good chance to see how Terraform can very easily fix such kind of issues or make complex changes to the infrastructure with just one command. So we go to the terminal and run Terraform plan-out plan. As you can see, Terraform detected that we need to move an EC2 instance from one subnet to the other. AWS cannot do that without destroying the existing EC2 instance and recreating it in the desired subnet. Terraform is going to do that automatically for us. So let's run Terraform apply plan. It's going to take some time, so let's speed up the video as usual. Once done, let's pay a second visit to the AWS console and see what has been done. As you can see, we have two instances named Bastion instance. The first one is terminated since it lived in the wrong subnet, so it had to go. The second one lives in the correct subnet. Let's have a look at its details. And yeah, the Bastion server now enjoys a public IP address that can be reached from the outside internet. Let's copy this IP address since we will need it to log into the server over SSH. To see how the Bastion server can act as a tunnel to log into the machines in a private subnets, we can just issue an SSH command as follows. SSH-J capital, which stands for jump server. Then we specify the username. Since we are using the Ubuntu AMI, the default username for this instance is Ubuntu. Then we paste the IP address of the Bastion server that we've just copied. The second server is the one that we want to connect to. Let's say that we want to connect to the auth server. So from the AWS console, we copy the private IP address of that machine, and in the terminal, we type Ubuntu then we paste the IP address that we've just copied. Running this command will prompt us to accept the identity of the remote server that we are connecting to. We need to accept that by typing yes. Since we are using the Bastion server as a jump server to the auth machine, we are making two SSH hops, one for the Bastion server and a second for the auth server. So we are presented with a second prompt. Again, we accept that. And we are inside the auth server. Let's log out of this server by pressing Ctrl+D. And we can repeat the same procedure for the other two servers. We just need to copy the internal IP address of one of them and paste it to replace the IP address of the auth server. Notice that now we are presented with only one prompt to accept the identity of the remote server. That's because we have already accepted the Bastion server's identity from before, so we're not prompted for it again. Let's test the final server in our stack by copying its private IP address and pasting it in the command. And here we go. So, this was a long lecture, but I hope it was worth your time. In it, we covered how we can use Terraform modules to create the EC2 instances that will host our application. We learned how to create the prerequisites of the EC2 instances, which are the security groups and the key pair. We also covered how we can use the Bastion server to connect to the machines that are unreachable from the public internet. That brings us to the end of this lecture. Thanks for watching. Hello everyone and welcome back. Our infrastructure is almost done now. We have the VPC, the subnets, the security groups, and the EC2 instances. But our application needs a database to store the user's data. There are generally two ways to deploy a database in AWS. Either manually install and configure a MySQL database on an EC2 instance, or to use the AWS Relational Database Service, aka RDS. As a rule of thumb, whenever there is part of the infrastructure that can be taken care of by the cloud provider, you should consider this as your first option. The reason is that the cloud provider will save you time and effort of the installation, configuration, best practices, security precautions, and performance tweaks that a MySQL database will need. Of course, the only consideration that you need to be aware of is the cost. Provisioning an EC2 instance that will host a MySQL database is relatively lower than opting for an RDS one. Accordingly, you should weigh your options based on the project needs, criticality, and budget. So, with that out of the way, let's see how we can use Terraform to deploy an RDS instance for our application stack. As usual, the first thing we need to do when deploying a new AWS component is search the Terraform registry for the existence of ready-made modules. Typing RDS in the search box, we can see that we have some results. Let's click on the first one. As we've seen several times now, the module page contains the source, the version, and a brief overview of what the module does and how it works. The RDS module needs two prerequisites so that it can work: the database subnets and the security group. So let's head to our main.tf file, and in the locals part of the file, let's define three new subnets. We already have the private and public subnets. Let's add the database subnets as follows: 10.0.201.0, 10.0.202.0, and 10.0.203.0. Then, in the VPC part of the file, we need to set the create database subnet group to true. The database subnet group name is DB, and the database subnets variable will take what we've defined in the locals part. So now we have the database subnets and the subnet group ready. The database subnets are where our database instance will reside. Notice that those subnets are not associated with an internet gateway or an NAT gateway. This means that they are only accessible from within the VPC. Obviously, this is a security precaution, since the database will not have any inbound or outbound access to the internet. Next, we need to create a security group that will allow access to the database. In the security groups part, we create a new security group. The name could be DBSG. The source is the same as the previous security groups that we've defined in the previous lecture: Terraform AWS modules / security groups / AWS. And the version is 4.17.1. The name could be DB. The description can be security group for the RDS instance. The VPC ID is taken from the VPC module the same way we did with other security groups. Then, the ingress with CIDR blocks would go as follows. From port 3306, which is a standard port of MySQL, the to port is 3306. The protocol is TCP. The description is MySQL access from within the VPC. And the CIDR blocks is the one we've defined in the locals part. So now we have the database subnets and the security group. Let's start creating the RDS instance. The module can be called DB. The source is the module that we've seen on the Terraform registry page.
The version is 5.3.0, which is the latest at the time of this recording. The identifier is the name we wish to give to this instance, let's say Modern DevOps DB. RDS supports several database types, for example MySQL, PostgreSQL, Oracle, and others. Our application is designed to work with MySQL, so the engine needs to be MySQL. The engine version can be 8.0. The family is MySQL 8.0, which is also the parameter group name. The parameters are values that are used to fine-tune the database engine. We don't need anything special here, so we'll just stick to the defaults. However, this module also allows you to modify the database parameters. Please refer to the module page for instructions on how to do this should you need to. The major engine version is 8.0, which also refers to a set of predefined options for the database. Again, we'll stick to the defaults. The instance class refers to the type and size of the instance that we are going to use. Let's choose the T4G small instance since we don't need a large one. We don't need a lot of storage for this instance. 5 GB is more than enough. The database can automatically expand the storage to a defined threshold. Let's set this to 5 GB as well. The database name refers to the name of the schema that we are going to create. This is different from the instance name. A single database instance can contain several database schemas. Once the instance is created, a new schema is created as well. Since our instance will contain only one database, let's give it the same name, Modern DevOps DB. The username here refers to the root user which will be created when the database is deployed. This user enjoys admin privileges over the entire database. It is highly recommended that we only use this user to create another less privileged user that the application can utilize. Let's name this user dbadmin. The database port is 3306, which is the default for MySQL. For high availability, we can opt to use multi-AZ, which deploys a database instance in each availability zone. We don't need this for this lab to minimize costs, so let's set this to false. Next comes the database subnet group. We need to take that from the VPC module where we defined it. The security group that this RDS instance will use is the one that we've just created a few moments ago. Now, some optional parameters. For example, the maintenance window, which is the time when this database can undergo maintenance when needed. We can set this to Monday from 12 a.m. till 3 a.m. When AWS wants to take a backup from this database, we need that to be from 3 to 6 a.m. The database needs to export the logs to CloudWatch. There are several log levels for the database, ranging from alert, audit, error, general, listener, and others. The log level defines the verbosity of the logs. We can set this to general, or we can just omit it to stop sending logs at all. Do we need to create a CloudWatch log group, or do we already have one? Let's create one. When the RDS instance is deleted, AWS takes a final snapshot from it so that we don't lose data by accident. But since this is a lab, we don't want to have a snapshot whenever we delete this instance, since this will take space and accordingly cost. Finally, we can set the deletion protection to true to prevent accidental instance deletion. But if we did that, we cannot use Terraform to delete the instance. Let's set this to false. There are several other parameters that this module can use. I recommend that you have a look at the modules page and explore the rest of the options that you can use to configure the database instance. Now, let's go to the terminal and run Terraform init since we've added a new module. Then we run Terraform plan-out plan. And seems that we have did something wrong. Let's check the ingress part of the database security group that we've created in the file. And sure enough, we have a typo. This should be ingress with CIDR blocks. So we fix that, and we move back to the terminal, and run Terraform apply plan. Notice that the RDS instance creation takes considerably longer time than the EC2 instances, so I will speed up the video till the operation is complete. So now the database is up and running. We can double check that by going to the AWS console, type RDS in the search box, and going to the RDS dashboard to view the running instances. And indeed, we have one running now. But how can we connect to this instance? We already chose the username, but we didn't supply a password. The password is automatically created for us when the database is deployed. To get it, we need to specify an output parameter. So let's go back to the main.tf file, And at the end of the RDS module, we can specify an output parameter. We can call it db password. The value of this parameter is db instance password, which is returned by this module. However, Terraform by default protects sensitive information like passwords, and it does not display them to the screen in clear text. Normally, we should not see the password. It should be fed to another module and stored in some safe place like HashiCorp's Vault or AWS Secrets Manager. But for now, we just need to connect to the database and make sure it works as expected, the same way we connected to the EC2 instances in the last lecture. So, to force Terraform to display the database password, we specify that sensitive is true. We also need to know the endpoint of the instance, that is, the URL that we can use to connect to the database. Thus, let's specify another parameter. We can call it the db endpoint and supply the value to be the db instance endpoint. Now let's go to the terminal, and to display the output values from Terraform, we don't need to reapply the manifests, and instead we can just run Terraform refresh. As you can see, we have the database endpoint displayed. But when it comes to the password, we can see that it was not displayed still. To display it, we need to rerun the command, only this time we need to instruct Terraform to return the output in JSON format. So we run Terraform refresh-JSON. The output is much more verbose since it is not meant to be read by humans, but rather by a machine, like it gets piped to another program. But since we just want to test connections to the database, we will come through the JSON output to get the password. And if we have a closer look at the output, we can easily spot the database endpoint as well as the password. Let's take note of both. Since the database instance is only reachable from within the VPC, we need to use the Bastion server to access it. So let's go to the AWS console, navigate to the EC2 dashboard, and check the Bastion server details. Let's copy the public IP address and return back to the terminal. Establish an SSH connection to the Bastion server by using SSH ubuntu add, then we paste the IP address of the Bastion server. Once we're inside, we need to install the MySQL client tool. This is by far the easiest way to connect to MySQL. So we run apt update, then apt install -y MySQL client. As soon as the package is installed, we can use it to connect to the database instance as follows. MySQL-u db-admin, which is the username, -h, then we paste the endpoint of the instance that we can get from the Terraform output above. -p, since we will supply a password. As a result, MySQL is prompting us to enter a password. So let's copy it from the output above and paste it here. And we are in. So, using Terraform on the RDS module, we were able to deploy a database instance that can be used by our application. The instance is hosted in the VPC and it can only be accessed by machines that live in the same VPC. In the coming lecture, we are going to deploy another piece of infrastructure, which is the parameter store and the secrets manager. We are going to use them initially to store the database endpoint and admin passwords so that we don't even need to show them to the screen for added security. Well, that brings us to the end of this lecture. Thanks for watching. Hello everyone and welcome to a new video in this class. Our infrastructure is almost complete now. We have everything except the load balancer, which would route the traffic from the public internet to our application. But before we start deploying a load balancer, we need to find a way to store the sensitive information that we have. For example, we have the database username, password, and endpoint. The password and endpoint are only known after the RDS instance is created. This means that we need to store them somewhere so that other parts of the stack can use them. AWS offers two solutions for storing values and sensitive values, the parameter store and the secrets manager. Before we start our lab, it would be worth our time to spend a few moments discussing the difference between both of them and when to use one over the other. Let's start with talking about their similarities and what both do well. So, they use KMS, which is short for Key Management Service. You can either use your own key or let AWS create one for you. In either case, the data is encrypted using a key, which is either created and managed by you and managed by AWS, or created and managed by AWS. They also use IAM policies to control which user account is eligible to encrypt and decrypt which values, which provides a fine-grained control level. Versioning refers to storing several versions of the same value. For example, if you use either service to store an application password, Then you change this password and then you want to access the previous password before changing. You can do that with the parameter store as well as the secrets manager. The cost model for each service differs than the other, but both of them charge 5 cents for every 10,000 API calls. All information security departments in all organizations will enforce some sort of password rotation policies. Password rotation refers to the regular change of application passwords for more security. Both services offer the ability to use custom logic for password rotation using Lambda functions. It works by simply creating a Lambda function that updates the password both on the application side as well as on the parameter store or the secrets manager part. Both services support this functionality. Now let's see how they differ. First and foremost, the secrets manager charges a flat fee for storing values. You pay 40 cents per month per secret. If you want to store standard parameters in the parameter store, you can do that for free. But for advanced parameters, this would cost you 5 cents per parameter per month. In the similarities part, we talked about secret rotation. We mentioned that both services allow you to use Lambda functions to implement custom password rotation logic. But the Secrets Manager offers native integration with some AWS services like RDS, Redshift, and DocumentDB. You also use Lambda functions for this, but the implementation is much easier. Additionally, the Secrets Manager supports cross-account secrets access, something that the parameter store does not provide. This makes the Secret Manager ideal for acting as a central place for storing secrets in a dedicated account. Other accounts, perhaps under the same organization, can use this account to grab the secrets. When it comes to how much storage capacity each service offers, the Secrets Manager can store up to 10 kilobytes of data per value. When it comes to the parameter store, that is brought down to 4 kilobytes for simple parameters and 8 kilobytes for advanced parameters. Additionally, you can save up to 500,000 secrets in the Secrets Manager per account per region. Parameter stores are limited to only 10,000 parameters per account per region. Finally, the Secrets Manager supports multi-region replication when working in multi-site environments. While you can achieve the same result with Parameter Store, the Secrets Manager offers this functionality out of the box. With Parameter Store, you need to arrange the logic for that yourself. Based on this brief discussion, we can safely assume that the Parameter Store can be used for casual parameter storage that does not require replication or key rotation. If you need a more serious replication-enabled solution that also offers rich support for password rotation, you need to go for the Secrets Manager. You'll also need to be aware that the Secrets Manager is considerably more costly than the Parameter Store, obviously because of the extra functionality it offers. Alright, so after covering what the Secrets Manager and the Parameter Store are, how they're similar and how they differ, let's see how we can integrate one of them into our infrastructure. As of now, we have parameters that we need to store so that they are available for the rest of the infrastructure components. The database username and endpoint can be stored in the parameter store since they needn't be encrypted and they're generally insensitive data. The database password that gets automatically generated for us can be injected into the Secrets Manager. The result is that the password won't be visible to anyone once Terraform is complete, and yet it will be available for whichever application that needs to use it. Now let's move to the IDE. Let's start by removing this output part since it poses a big security risk to show the RDS password in the returned output. To add parameters to the parameter store, we don't need a module since it's as simple as using just a single resource. The resource name is AWS SSM parameter. The name could be DB endpoint. The resource takes 3 inputs. First, we need to specify the parameter name. This is where you will need to follow the naming convention that your organization uses. It could be something like moderndevops.db.endpoint. We start with the project name, then the component to which the parameter belongs, then the specific value, which is the endpoint. The type of this value is string. And of course, the value is the RDS instance endpoint that can be brought from the module. Let's add a second parameter that we want to store. Again, we use a resource of type AWS SSM parameter. This time we can name it DB username. The parameter name in the parameter store can be moderndevops.db.username. The type is string. And the value, well, we can just hard code the database username that we've used in the DB module, but then we would be repeating ourselves. Let's move the DB username to the locals part of the file. And in the DB module, we can refer to the locals variable like local.db_username. Now we can easily refer to the same value in the parameter store. The third value that we need to store is the database password, which we are going to use the secrets manager for. Notice that we could equally store it in the parameter store and encrypt the value. It would provide the same outcome at no cost. But for the purposes of demonstration, we are using the secrets manager just to show how we can deploy one using Terraform. But in a similar environment that runs on production, we could have gotten away with the parameter store for all our values. To create a secret in the secrets manager, we need two steps: creating a secret, then creating a value for that secret. So we use the Terraform AWS Secrets Manager secret resource to create the secret. We can call it DB password. We only need the name for the secret. We can call it moderndevops.db.password. Then, to actually store some value in that secret, we use the AWS Secrets Manager secret version resource. We can call it again DB password. This resource needs the secret ID, so we can just get it from the outputs of the AWS Secrets Manager secret resource that we've just created. We also need the secret string, which is the actual password that the RDS instance generated. This can be brought from the outputs of the RDS module that we've used earlier in this file. And that's all what we need to store the database endpoint, username, and password in the parameter store and the secrets manager of AWS. Now let's move to the terminal. And notice that we needn't run Terraform init since we are not introducing any new modules in this part of the lab. So we just run Terraform plan-out plan as usual. Then we just run Terraform apply plan. The process takes only a few moments to complete. We can go to the AWS console, have a look at the parameter store by typing parameter store in the search box. Once we are in the parameter store dashboard, we can check the parameters that we have. And as you can see, we have the database username and the database endpoint parameters correctly deployed. Let's check the database password by typing secrets manager in the search box. And we move to the secrets manager dashboard. Click on the secrets from the left navigation bar. As you can see, we have our secret. We can check the value of that secret, which is the database password that was generated for us, by revealing the encrypted value in clear text. Now, let's see how we can retrieve our database password from the secrets manager. Obviously, this step would be assumed by the tool that would be used to deploy the application and configure the database. But in case someone needs to log into the database for debugging purposes, this is how they can retrieve the database password. From the command line, we can run AWS Secrets Manager get secret value --secret ID. Then we type the name of our secret, which is moderndevops.db.password. As you can see, the output is in JSON format. We need to extract the password part from this object. If we are using code in any modern programming language, for example Python or Go, it's pretty straightforward to do this. But even if you're on vanilla shell, there are tools to do this task, and they are also not that complex. We just need to install a package called JQ. On Ubuntu, we can just use apt update. Followed by apt install -y JQ. On a Mac OS, you can use brew, while on Windows, you can just use Chocolatey or the package manager of your choice. Once JQ is installed, we can repeat the same command, but this time piping the output to JQ. We use the -r argument so that the output is not surrounded by double quotes. This can be of some importance if you are piping the output to an even third command. Then we start our query with a dot, which represents the root of the object. The key that we are after is the secret string, so we type that. And as you can see, we have the database password. So, in this video, we discussed how we can make use of AWS's Secrets Manager and Parameter Store to save our sensitive and non-sensitive values in a central location that is hosted by AWS. Notice that this is not the only way we can store data centrally. We could have used a solution like HashiCorp's Vault. However, using AWS's managed services makes user and access management consistent with other applications hosted on AWS. Well, that brings us to the end of this lecture. Thanks for watching. Hello everyone and welcome back. For our application to receive any traffic from our end users, we need a load balancer. The purpose of the load balancer is twofold: to provide a gateway for traffic coming from the external internet to our application that is hosted in the private subnets, and to provide high availability by distributing the traffic to multiple machines. In this part of the lab, we are only demoing the first benefit, which is having a gateway for our application. AWS offers three types of load balancers: the Classic, which is now deprecated, the Application, and the Network load balancers. The Application load balancer is a Layer 7 HTTP server. It understands the HTTP protocol and thus can provide features like routing by headers or host names. It also supports session stickiness. When session stickiness is enabled, the load balancer remembers which connection landed on which server upstream. If the client wants to re-establish the session, the load balancer makes sure the previous server handles the connection. This can be useful, for example, when the application needs the user to log in and saves the login data on the server. If another server receives the connection request from the client, it may require them to re-login. So obviously the application load balancer should be your first choice when you're running an HTTP application. But if you're expecting non-HTTP traffic, or if you don't care about the contents of the HTTP packet, like the header, the host name, or the session, then you can opt for the network load balancer. NLB works on layer 4 of the TCP/IP protocol. Accordingly, it can work on any TCP protocol, including HTTP. However, it won't offer the HTTP features that the ALB provides, like session stickiness, for example. NLB is cheaper in terms of cost and is generally faster than ALB. It can also scale faster. You may opt for NLB if your application does not use HTTP as a network protocol, for example, a database or a mail server. It could also be a better choice if you just care about speed and scalability more than intelligent routing. Alright, so that was a brief comparison between the different load balancers that AWS provides. For this lab, we are going to use the ALB since our application uses HTTP and we want to make use of the HTTP features that the ALB provides. ALB is a complex component that is better handled by a Terraform module. So, as we are used to by now, when we need to use a Terraform module, we start by searching the Terraform registry for the existence of a ready-made model. Going to the Terraform registry and typing ALB in the search box, we have a look at the results and click on the first one. As you can see, we have a page that contains the source of this module and the latest version as of the time of this recording. We also have some usage instructions about how we can configure this module to our preference. I've already gone through this for you, so we can just start coding. However, and as always, if you want to fine-tune the module to your own project requirements, please visit this modules page for the details. Now, moving to our IDE and the main.tf file. At the end of the file, we start a new module. We can call it ALB. The source is Terraform AWS modules /ALB/AWS. And the version is 8.3.1. The load balancer type is application. We've already discussed the different types of load balancers that AWS supports at the start of this lecture. The load balancer needs the VPC ID, so let's get it from the VPC module outputs. It also needs at least 2 public subnets that are hosted in 2 different availability zones. We can just point it out to the 3 public subnets that were created for us by the VPC module. The ALB also needs a security group, since at the end, the load balancer is just several machines that perform reverse proxying. They must be placed in internet-facing subnets and have a security group that defines which traffic is allowed to them. We could create a new security group specifically for the load balancer, but a more straightforward option would be to use the default security group that is built in for any VPC. Then we can just attach the needed rules from within the load balancer module itself as follows. We use the ingress all HTTP input object that the module accepts. The type is ingress since we are referring to traffic arriving at the load balancer. The from port is 80, which is the port that will be facing the public internet. The to port refers to the port on which the upstream server is listening. The upstream server is the machine that will be receiving traffic from the load balancer. In our case, this is the UI server, which is listening on port 3000. The protocol is TCP. The description could go as HTTP web traffic. And the CIDR block that this load balancer is allowed to listen to is any IP address. We want our load balancer to receive traffic from anywhere on the internet. In more controlled environments, or if this is a development environment that you don't want accessible to the general public yet, you may want to specify specific IP addresses or IP address ranges that are allowed to access the load balancer and hence the application. But for demo purposes, let's just leave it at 0.0.0.0/0. The security group also needs an egress rule. So egress all is the name of the object that this module expects. The type is egress, which refers to traffic leaving the load balancer to the client's device. The from port here is 0, denoting all ports. The to port is also 0. The protocol is -1, which means any protocol. And the CIDR block is also 0.0.0.0/0, which means any IP address in any range. We want our load balancer to be able to communicate with all the clients. With that, we have our security group and its rules out of the way. The next thing we need to configure is the listeners. The listener is how the load balancer should react to traffic arriving at a specific port. We want the HTTP traffic arriving at port 80 to be routed to the UI instance. So we define the list of HTTP TCP listeners. The port is 80. The protocol is HTTP. And the target group is 0. The target group here refers to one or more EC2 instances that are meant to receive traffic arriving at the load balancer. It's like a receiving party. But the target group is more than just an abstraction of a bunch of machines. It can do health checks to make sure that traffic is only routed to up and running servers. 0 here refers to the index of the target group that we are yet to define. The target groups, as we will see in a second, live in a 0-based list, with 0 referring to the first item. Thus, let's define the list of target groups that we have. The name prefix could be anything. Let's say H1, which is taken from the example in the module documentation. The backend protocol is HTTP, which is the protocol that the target group will use to communicate with the EC2 instance. The target type can be an IP or an instance. If your target is not an EC2 instance, for example, an internal load balancer, a database, or a Fargate container, then you can use IP as the target type. But if your target has nothing but EC2 instances, then it makes sense to set the target type to instance, which is what we are going to do. Deregistration delay is how long the load balancer would wait for an instance that is deregistering. When you want to take an instance out of the pool, the load balancer stops sending new requests to it. But it also needs to wait for some time for existing connections to finish. Otherwise, clients may experience a sudden drop in the connection, which doesn't help provide a good user experience. To avoid that, the load balancer waits this number of seconds till all existing connections are terminated. This is also referred to as draining. We can set this to 10 since our application does not establish long-running sessions with the clients. For example, we don't accept file uploads, and we don't do any video streaming. Feel free to change this value according to your specific project needs. Next, we need to specify how the target group will perform health checks against the instance. First, we indicate that we need health checks to be enabled for this target group. The interval specifies how frequently the target group should check on the target server. We can set this to 30 seconds. The path refers to the URL that the target group would hit to make sure that the application is running correctly. Some applications dedicate a specific endpoint just for health checks, for example, /healthz. The application code performs self-checks on all the programming logic and makes sure nothing's wrong with any of the other endpoints. Then the result is conveyed through the /health path. In our case, our application is not that complex, so we just need health checks to hit the root of the URL. The port is the port on which traffic is received. We can refer to that as the traffic port, which is 3000. How many times should the target group hit the URL and receive a successful response before considering the target as healthy? The default is 5 times, but let's make them 3 to shorten the time duration needed to bring the target into the pool. Similarly, how many times should the target group receive an invalid response from the health check before it considers this instance as down and removes it from the pool? Again, let's set this to 3. You are advised to change those values depending on your business requirements. What if the target instance did not reply to the health check probe at all? The target group can wait for a specific number of seconds before giving up and marking the instance as down. I guess 6 seconds is more than enough for a request to be fulfilled. If the server takes more than 6 seconds, then it's most certainly down. The protocol in which health checks will be performed is HTTP. Now comes an important setting called matcher. It defines which HTTP response codes are considered valid and which are not. If you have some HTTP background, you'd know that any response code that starts with 2 is considered a success of some type. Anything that starts with 3 is some sort of a redirect, which is still considered a valid response. The server may want to direct you to the login page when you are accessing the root URL, which is in fact what our application does. Responses that start with a 4 or a 5 are errors. We're not interested in whether the error is on the server side, which is denoted by 500 and something, or that the page is having trouble being found or loaded. In all cases, a 4 something or a 5 something response code is an invalid response, and the server should not be receiving traffic. With that, we end the health checks part of this target group. We need to specify the protocol version that this target group is using. It's HTTP version 1. Currently, there is HTTP version 2 and even version 3 started getting some traction. But to make things simple, our application is using HTTP version 1. Finally, we need to specify the actual targets that this target group will work with. For the current part of the lab, we only have one instance, which may stir some valid questions in your head. For example, if we are using just one instance, then what's the use of a load balancer? Where is the high availability? Why are we even using health checks if we are only using one server that will get pulled out of the pool if it is down, with no other servers to handle traffic? If you have those questions, then congratulations, you have the mindset of a system architect, which is of course a skill that is always in high demand. As for the answers to your valid questions, yes, for the time being we are not supporting high availability, but later down in the class we will see how we can achieve that after we deploy our application. For the time being, our target is the UI instance. We can call it UI to be descriptive. The target ID is the instance ID of the EC2 instance, which can easily be brought from the EC2 module. And the port again is 3000. It makes sense to refactor the code and put the ports in the local spot of this file so that we can just refer to them and they can be changed easily when we want to. Well, we'll definitely be refactoring this code later on. I just want you to focus and understand the core concepts represented here. So now we have the load balancer code ready, let's put it into action. But before we start deploying our load balancer, we need to take care of something. Currently, none of our instances have any servers running. This means that if we deploy the load balancer and the target group starts probing our UI instance, it will time out, marking the instance as not ready. In other words, we won't be able to verify that the load balancer is running correctly and that we can use it to have valid content from the UI instance where part of our application will be running. So to address this issue, we can just install a dummy server. Anything that listens on port 3000 and returns a valid HTTP response would do the job. Let's go to the AWS console and grab the IP address of the Bastion server. Then, in our terminal, we establish an SSH connection, placing the Bastion server as a tunnel. Our target instance is the UI machine, so let's go back to the AWS console and grab its internal IP address. Then, in our terminal, we paste this IP address as our end target. Then, inside the UI server, let's run apt update to refresh the repositories. Once done, let's install Nginx. Nginx is a web server that will return valid HTTP response to the load balancer so we can make sure that everything is running correctly all the way through. So we can run apt get install -y so as not to be prompted to accept package installation, then Nginx. In a few seconds, the package is deployed. Nginx listens by default on port 80. We need to change that so that the server listens on port 3000. For those of you who are lost and do not know what we are doing, we are just running a server that listens on the same port that our application will listen on when deploying it. The thing is, we haven't deployed our application yet, and we need to test that the load balancer is configured properly. To change the default port on which Nginx listens, we need to edit the file under /etc/nginx/sites-enabled/default and modify the port from 80 to 3000 before saving the file. Then we need to restart the server to apply the new configuration. Let's just do a little test before we log out of the server. Using curl, we can initiate a GET request to localhost :3000. And sure enough, we receive some HTML back, which means that the server is running and listening on port 3000 as it was configured to. Now, let's log out of this instance and start applying the Terraform code. Since we have a new module added to the code, we need to run Terraform init to download the module code and make Terraform aware of its existence. Then we run Terraform plan-out plan as we're used to. After which we run Terraform apply plan. The load balancer takes some time to get deployed, so I'm speeding up the video to save the lecture time. And seems that we've missed something in the code. Let's see. Okay, we didn't specify the backend port in the target group, so let's do that quickly. The backend port is where the target group would direct the traffic that it receives. In our case, this is port 3000 where the UI server is listening. Now let's run Terraform plan-out plan again. Then Terraform apply plan. This time it shouldn't take long since it's just creating the target group. If we go to the AWS console, and if we are still in the EC2 dashboard, we can just click on the load balancers link on the left-hand navigation. And as we can see, the load balancer is in the active state. It normally takes a minute or two to move from the provisioning state to the active one. Now let's visit the target group that we've created. As you can see, we have the target group, and it has only one target, which is the UI instance. Again, it may take some time for the health checks to pass successfully, and the instance is in a healthy state. Refreshing the page, we see that the instance is in healthy state now. So let's go back to the load balancer page to see if it's working properly. To test it, we just need to copy its DNS name from the console and open a new browser tab and paste the DNS address. As you can see, we have the Nginx welcome page displayed, which means that the load balancer was able to connect to the upstream UI instance and get back the response to the client. So, in this lecture, we started by laying out the different load balancers that AWS supports and why we are choosing the application load balancer as our target offering. Then we learned how we could use the ALB Terraform module to deploy an application load balancer. We also discussed the concept of target groups and how health checks help make sure the client is only served by healthy servers. That brings us to the end of this lecture. Thanks for watching. Hello everyone and welcome back. We kind of have a complete infrastructure by now, right? We have a VPC with the required subnets, our EC2 instances are hosted in the private subnets, we can reach them through the Bastion server, we also have an RDS database where we'll be storing our user data. The database username, password, and endpoint are stored centrally in AWS through the secrets manager and the parameter store. And in the last lecture, we deployed the load balancer, which acts as the entry point for our application. We've even deployed a dummy Nginx server so that we can see some content when we want to test our load balancer. But as you notice, in the previous lecture, we had to use the ugly-looking DNS address of the load balancer to reach our application. This will get us nowhere when we want to invite the users to visit our application, will it? We need to have a professional DNS name that we can use in our marketing campaigns. Something like weatherapp.somedomain.com, right? Let's see how we can do that in theory first, then discuss the technical implementation using Route 53 as our DNS manager. So, assuming that we want to communicate with a server that has the address of www.example.com. I'm not sure if you are already aware of this fact, but any DNS name must end with a dot. Yes, that would be www.example.com dot. You almost never find this dot in any DNS address because all servers and clients assume that it's already there. If you want to try, you can open your browser and type any address ending it in a dot. For example, www.wikipedia.org dot. The browser will not complain because, in fact, if you did not add this dot at the end, it will add it for you behind the scenes. You've just saved the browser an extra step that it would do, and it will gracefully open Wikipedia's front page for you. This is actually how DNS works. It's like an inverted tree that starts at the root, which is denoted by the dot. Then you move backwards to more specific parts of the address till you reach your target, which is on the left-handmost side. Each part of the address is either a record or a zone. A zone is like the dot, which is the root zone, the com, and example in this demo. But www is not a zone. It's a record that should return a valid IP address that the client can use for communication. But how can part of the address be regarded as a zone versus a record? Well, it simply depends on how the DNS server responds to your request. So if you are requesting www.example.com, the DNS server will reply to you with the IP address of the www machine as it is configured in its zone records. If it replies with some name server, then this is a zone, not a record, and you should ask one of the name servers that it replied with for the IP address of www.example.com. Now let's see how the process goes, start to finish. I'd like to stress here again that what I'm going to narrate here is purely theoretical. In the real world, while the concept remains the same, there are many aspects that make this process faster, more secure, and more efficient, like DNS caching, for example. But for the purposes of this lab, and for all of us to be on the same page, let's see how a typical DNS request takes place. No caching, no performance boosts, no fancy stuff, just plain theory. When a device on the network requests an address like www.example.com, it first consults the DNS server that it is configured to use. Assuming that this DNS server has no knowledge of any other DNS servers upstream, it connects to what's called the root servers. The root zone has the name servers for other zones like com, org, edu, net, info, and others. When your DNS server asks the root servers for com, it receives a reply that contains the name servers responsible for managing the com zone. So your DNS goes and asks the com name server about example.com domain. This is where the com server responds with the name server that is managing example.com. This name server is special here because it is available for companies like GoDaddy, Namecheap, Google, and even AWS. Yes, you can use AWS to rent you a domain for a fee, just like other companies. The company in this sense is much better known as a domain registrar. It is the owner of the domain, and it manages its DNS records. Let's say that the registrar that handles example.com is GoDaddy. The DNS goes to the name servers of GoDaddy and asks for information about www. If this is a record, then GoDaddy will reply with the IP address of this record. The DNS server returns that IP address to the client so that it can establish communication with it. It also caches this IP address for some time so that when the client requests it again, it doesn't need to go all that path, but that's out of our scope. Now, what if you want to create a zone called www in the example.com domain and we want another DNS server to manage this zone for us? This is possible. Actually, this is how DNS works, as we saw in the previous slide. It is referred to as domain delegation or zone delegation. All you need to do is create a zone in your DNS server. In our case, that would be Route 53, AWS's DNS management service. Once you do, the DNS automatically creates 4 name servers for you. You need to copy them somewhere. Then, in GoDaddy's DNS server, you create 4 records of type NS, which is short for name servers. And you paste what you've copied. The name of the record will be www. Now, in Route 53, you can create an A record that resolves to www.example.com and give it an IP address of one of the AWS services that Route 53 supports. This could be an EC2 instance, an alias for the load balancer, a CloudFront distribution, and many others. This way, Route 53 becomes the DNS server for www. Additionally, you can add child records under this zone. For example, dev.www.example.com. Of course, it doesn't make a lot of sense since www is not suitable for a zone name, but rather a record. But you get the point. So, what does this have to do with our class and our lab? Well, I happen to own a domain called fekarani.com that is hosted on GoDaddy. You can create a zone in Route 53 called Weather App, then copy the resulting name servers to GoDaddy. We can use them to create 4 NS records on GoDaddy, effectively directing any DNS requests for weatherapp.fekarani.com to Route 53. The result is that we can use Route 53's integration with other AWS services like the AWS Certificate Manager. In fact, we can also create subrecords under the zone, like for example, dev.weatherapp.fekarani.com, staging.weatherapp.fekarani.com, and so on. So, with the theory out of the way, let's see how we can do that in practice. Going to our IDE, we start by creating a Route 53 zone. Again, this is one of the components that do not require a module, just a Terraform resource. The resource type is AWS Route 53 zone. The resource name can be Weather App, and the zone's name is Weather App. We need to get the name servers that this zone will return, so we specify an output parameter. The name can be zone NS. The output value can be AWS Route 53 zone, which is the resource name, followed by name servers. This will return the name servers of the zone once it gets created. So let's go ahead and create this zone by running terraform plan-out plan, then terraform apply plan. It shouldn't take long, but once done, we have the name servers printed to the screen. If you want to follow with me in the next step, this depends on whether you own a domain name and which registrar is managing it for you. If it's GoDaddy like me, we can just log into the DNS manager of your domain. Then create a new record. The record type is NS, short for name server. The record name is Weather App, which is the zone name. We need to create 4 records corresponding to the 4 name servers that our Route 53 zone has returned. So I'll just go ahead and add them one by one. Once done, let's go back to our IDE and create a zone record. The record here should point to the load balancer that we've deployed in the last lecture. Again, this doesn't need a module. A single Terraform resource is enough. The resource type is AWS Route 53 record. The name could be www or just anything really. We need the zone ID of the weather app zone, so we can just grab it from the resource that we've just created. The record name could be the root of the zone, that is weatherapp.fakarani.com, or it could be a subrecord like www.weatherapp.fakarani.com. For the sake of keeping the URL short, let's just stick to the root of the zone, which is weatherapp.fakarani.com. Later, we may change this when we start working with multiple environments. The type is an A record, but this does not resolve to an IP address, but rather to a load balancer. AWS has built-in integration between Route 53 and the application load balancer, so we need to invoke the alias input. It needs the DNS name of the load balancer, which we can have it from the outputs of the ALB module. It also needs the zone ID, but notice that this is not the Route 53 zone ID that we've just created. It is rather one of the properties of the application load balancer, which is also called the zone ID. Let's grab it from the outputs of the ALB module. Do you want to evaluate the health of the target? Yeah, why not? Notice that Route 53 can act as a load balancer. Obviously, it doesn't come with the bells and whistles of a service like the AWS application load balancer. However, it can come handy when you have multiple targets for a single record, but that's out of our current scope. For this lab, it will only make sure that the load balancer is returning a valid response before connecting it to the client. The reason is that if the load balancer is down, it will save the client the time it needs to keep trying till it times out, which is a nice user experience setting. Alright, so we're ready now to create our record. Hopefully the new zone that we've added to GoDaddy is in effect now. It usually takes a few seconds, but sometimes it takes minutes or even hours to update. So we go to the terminal, we run Terraform plan-out plan since we don't have any new modules. Then we run Terraform apply plan to create our record. This operation should take some time. Once done, we can open the browser and navigate to weatherapp.fakarani.com. And here we go. In case you're wondering why we are seeing an Nginx's web server welcome page, in the previous lecture we deployed it as a dummy server listening on port 3000 so that we can test the load balancer's functionality. Again, sometimes it takes considerably long time for the DNS propagation to complete. If you followed that lab using your own domain and you still get a DNS resolution error, just give it some more time. You can also use some command line tools like nslookup or dig for troubleshooting. Alternatively, there are online services that can check the DNS resolution chain for you. One of them is dnschecker.org, which would check the DNS propagation across different countries so that you have an idea about the progress. We just want to make sure that Route 53 is the designated DNS server for managing the zone. Then we created a Route 53 zone under a domain that I own for our application. We needed to update the DNS records of the parent domain by adding the NS records of the Route 53 zone. Then we added weatherapp.fakarani.com as a record in our zone and used the load balancer alias to integrate it with Route 53. Now we can access our application when it gets deployed using a nice, fully qualified domain name instead of the auto-generated one from the load balancer. Well, that was all for this lecture. Thanks for watching. Hello everyone and welcome back. Our infrastructure is now built and it is ready to host our application. There is just one final step that we need to take, which is deploying an SSL certificate. Today, no web application runs on HTTP. In fact, if you came across one, you should be very careful when browsing it and by no means supply any personal or financial information of yours. This is simply because the HTTP protocol is transmitted in clear text over the wire. Anyone can scan the packets and reveal whatever information that comes from your browser to the server. Our application doesn't require any personal or financial data from the users, but your use case may be different. In all cases, it is considered as best practice to always run any publicly accessible web server over HTTPS. So, let's briefly discuss how HTTPS works. When the client initiates a connection to the web server over HTTPS, the server presents a certificate to the client. The certificate contains identity information about the server, most importantly the host name. The client trusts this certificate if it is signed by a certificate authority that is known to the client. All major browsers have built-in CAs. They just ship with the browser when it gets installed or with the browser that comes with the operating system. This increases your credibility and provides a better user experience in general. So why do we need to use HTTPS for our web communication? Well, even if our application doesn't accept sensitive or financial information from the clients, we still need to enable HTTPS. Using SSL increases the client's trust in our web application and helps with website credibility. It also gains the client's trust, which provides an overall higher level of credibility. So now we have the motivation to deploy an SSL certificate to the application. Let's review our available options. To purchase a certificate, there are many certificate authorities that we can use. For example, DigiCert, VeriSign, GeoTrust, to name a few. There is also a free alternative from Let's Encrypt. But since we are using the application load balancer from AWS, we are eligible for a free certificate that is managed by AWS using its certificate management service. The advantages of following this path are as follows. First, we won't be charged for using the certificate since we are deploying it to an AWS server. We also have a seamless integration between the certificate manager and Route 53. As we will see in a few moments in this lab, to have a certificate, you need to prove domain ownership by placing specific records in the DNS zone that you have. ACM can do that for us automatically since our zone is already managed now by Route 53. Finally, the certificate renewal is also taken care of for us by AWS. With any other alternative, we need to handle renewal ourselves. Let's now see how we can do that using Terraform. ACM has a module that we can make use of. So if we go to the Terraform registry and search for ACM in the search box, we have a list of results. As usual, let's pick the most popular one. We have the module, the version, and the usage instructions. Let's move to our main.tf file in the IDE, and at the end of the file, we create a new module. We call it ACM. The source is Terraform AWS modules /ACM/AWS. The latest version at the time of this recording is 4.3.2. The module expects the domain name for which we need the certificate issued. That should be weatherapp.fakarani.com. The certificate manager needs to verify the domain identity by inserting specific records in Route 53. But to do this, it needs the zone ID, so let's specify it. We can easily get the zone ID from the output of the AWS Route 53 zone ID. Certificates can also be used with the subject alternative domains, or SAN for short. This specifies the extra domains that this certificate can be used to validate. Using SAN, we can create what's referred to as wildcard certificates. A wildcard certificate can validate any host name that falls under the domain in question. It is denoted by *weatherapp.fakarani.com. With that, this certificate can be used to validate anything .weatherapp.fakarani.com. For example, dev.weatherapp.fakarani.com. But be aware that it can only be used for one variable part of the domain name. For example, it cannot be used for dev.weatherapp.fakarani.com because now we have two variables, dev and dev. Finally, we need to wait for the validation to succeed. What would happen now is that the ACM will insert some CNAME records in the Route 53 in the zone that we've specified. Then it would check that the records are there, which is a proof that we have ownership of that domain. The certificate is not valid unless ACM verifies domain ownership. Since we need to use this certificate in other parts of the code, we need to wait till it is validated and ready to use. This is all the code that is needed to create an ACM certificate, but how can we use it with a load balancer? Let's move back to the ALB module code. In the HTTP listeners part, we need to do two things. First, we need to remove the target group index since the HTTP traffic that we are receiving on this listener would not be forwarded to the target group. This is where our second step comes. We need to configure the HTTP listener to redirect the connection to the HTTPS port. This way, when a client requests our website over HTTP, the load balancer will automatically redirect the connection to HTTPS. So the action type should not be forward, which is the default, but redirect instead. But now we also need to configure how the listener redirects the traffic. So we introduce a redirect object. The port to redirect to is 443, which is the HTTPS port. The protocol is HTTPS. The status code that the load balancer will respond with is 301, denoted by HTTP 301. Now we need to introduce the listener that will actually receive and process the HTTPS traffic. So we define the HTTPS listeners, which is a list. We only have one listener. The port is 443. The protocol is HTTPS. The most important part, however, is the certificate ARN. We can get it from the outputs of the ACM module. The target group is 0, which is the first and only target group that we have. And that's it. Now it's time to apply our code and see the results. In the terminal, we run Terraform init since we are introducing a new module. Then we run Terraform plan-out plan, followed by Terraform apply plan. The process will take some time, especially since Terraform needs to wait for the ACM to verify the domain ownership. Once done, let's verify the results. We go to the web browser, and if we still have the application page open, we just need to hit refresh. As you can see, we are immediately redirected to the HTTPS version of the connection. We can clearly see that since we have an icon that denotes HTTPS beside the URL. We can click on this icon and see the details of the certificate presented to us by the load balancer. As you can see, it is signed by AWS. So, in this lecture, we started with a brief discussion about HTTPS, why it needs to be used, and how it can be implemented. Then we added the necessary Terraform module that would create and validate the server certificate. We also modified the load balancer so that it uses the certificate created by the ACM. And that was the last piece of our infrastructure puzzle for the first environment that we are building in this class. So, congratulations! That brings us to the end of this lecture. Thanks for watching.